Oh, it was a smart contract article. I remember.
Oh, okay. I actually haven't read that one yet.
Yeah, yeah, a
Um,
smart contract article.
So we are probably being recorded by YouTube and Rumble both right now,
yeah, just
just so you're
FYI,
aware.
Mike. Um, so
But that this is the you you don't quite know when a dual stream's going to hit all endpoints. So
right, it's usually about 30 seconds, at least when I've
yeah,
watched your streams afterwards. So probably by now we're live.
yeah,
Um,
it looks like we're up. YouTube's saying that we are, but I'll let the
okay,
timer
yeah.
count down. And here we are.
Alrighty. Hello, everyone. My name is Peter Harpending. Today we are talking about how the matrix can multiply, and it's the shocking truth that big data doesn't want you to know. Heartbreaking, part one. And here we have big data pictured. He's playing.
I like how it's data that's just fat.
Yeah.
You,
Well,
you made Brett Spiner expand more than he has from age.
I don't know. I mean, he's looking. I mean, this is a cropped picture, and the full picture. Well, the full picture, I was starting to get model collapse because I kept giving it too many things, and like you can tell, the lighting's kind of getting wonky. But you know, there's a lot of rats. There's an anthill. He's got, he is representing Ruffles though. Anyway,
I forgot. I forgot
and
these things exist.
and Cheetos and Cheetos. I wonder if AI. I wonder if that's like part of their revenue model now is like doing
Product placement.
product placement inside of your AI images. Oh
You know
yeah,
what's crazy?
here's
Because
your
it can't.
family photo with you using, eating Ruffles potato chips.
Right. Well, what's amazing to me is that like I can read original. Like the letters aren't all AI messed up looking.
Yeah, yeah,
And
it's gotten a lot better. I mean, I remember when it couldn't do text at all, and
so
hands, it really struggled with hands.
the other day, Selena ordered Natsumi a shirt um online that she thought looked cool, and it came, and it's just a t-shirt with like a printed thing on the front that looks kind of like a cool logo, but if it's not, it's just AI. It's an AI generated gibberish print
Mm,
that's on
yeah.
a t-shirt that you can buy, and it's hilarious. So it's now my favorite t-shirt. I want one.
AI t-shirts are like the kanji tattoos of the 2020s.
Yes. Where people walk around with like, hey, what's that mean? It means depression, bro. And you read it and it says like economic downturn. And I'm like, okay,
Yeah, yeah.
you can just, you know,
Mike has a giant big tribal tattoo on his back
well, at
in
least it won't accidentally say something.
yeah. Um,
Like, I saw a Chinese tattoo on a guy's calf the other day that said "I pee in public," and he didn't know
dude,
that.
dude, do you know how many people probably with AI like now like you can't read Chinese, and like you don't know enough about Chinese to even like go look up what the character means, but
Mhm.
now you can like take a photo of it and ask ChatGPT what it says, and it'll say that means economic downturn.
Dude, oh my
There's
God, there's
so
going to
many
be like
people. There's so
ego
many people.
sabotage.
Oh, dude.
There's so many people that are going to take a picture of their tattoo and ask, like Gemini is just going to auto, like on their phone. Gemini is just automatically going to be like, "Oh,
Oh,
that
dude.
says blah." There's
Dude.
there's
Mm.
that dude. We need to get in the tattoo removal business. This is like probably boomtown right now
Oh, dude.
for like wacko foreign language tattoos. Like that's got to be a huge thing with like ridiculous Chinese tattoos. Just Chinese characters. There's got to be tons of them.
Dude. All right.
I do like that. That's really funny though.
Yeah. Anyway, so this is big data. He's staring into the matrix, and he's concerned that the matrix can multiply.
With a
Um,
game controller.
Yes, well, that he controls the Matrix.
Well, he's in. Does he have an avatar in the Matrix? Like, you know?
No. Big Data is the guy that like runs the Matrix. This is how he does it.
And that's his inputs.
Yeah, and that's why he's so fat, dude. He can't leave. It's a full-time job.
Oh, he's like a Reddit mod.
Yeah. Okay.
Very nice.
Why are you laughing, dude? I feel bad for him.
But
Yeah. And look at his face. He looks so horrified. Okay.
I can just hear Dr. Now talking to him.
Well, Data, the pattern that's been established is you have a toxic dynamic with your matrix moderation.
Anyway, I've never actually watched Star Trek, so I just remembered that Data was a character.
Next Generation's the best one.
All right, you've told me that before, and I keep meaning to watch it. And anyway,
it's good.
So disclaimers. I am going to default to under-explaining things because math is complicated and there's a lot of it. And so your end of this bargain for both of you is you have to be very aggressive about asking me questions when you don't understand something. So want to mitigate the scope creep. I don't know what you guys are not going to understand. If it's up to me, I will spend like 2 hours explaining the concept of coordinates and then like completely brush over, some really complicated concept in cryptography that is just obvious to me because I deal with it all the time. But like coordinates, that's a really complicated concept, right? Well, the thing that you learn in both math and programming is that complexity isn't really your enemy, it's subtlety. Subtlety is what's going to get you. And anyway, so setup here is we have this table that I got from Google.
I like how sex is an integer, so you can have all 72.
Yeah, well, in this data, unfortunately, we only have sex 0 and sex 1.
Boy.
So we have a table of height and weight measurements for these persons. And so we have, I don't know who is 6 feet tall and 155 pounds.
A girl?
No, that's sex 0. These are obviously the men.
Okay.
Anyway,
those are some light men.
Yeah, so well, this person's only 5'7", and like that's a decent weight to be if you're 5'7". But anyway, so there's two different types of numerical variables here that are encoded with numbers. So we have sex, which is a categorical variable. We would call that an enum type, and it's pretending to be a number. And height and weight are actually numerical values, right? And it's very, very important. You've done tons of work with databases, and people putting zip codes as an integer. Zip codes are not an integer, right?
Yeah. And then they changed the standard on you.
Oh, right. So, using our brains, we can surmise the following. So the data includes the sex variable because men and women probably have different respective relationships with their height and weight. Taller people are probably, in general, heavier than shorter people, and we should also verify that these things are true. So the first rule of large data analytics is to always visualize your data. And so we can see here that gender 1 is generally smaller and gender 0 is generally larger. And the second rule of large data analytics is to always draw the best fit line, right? So we have gender 0, we have gender 1, and then we have this best fit line. So the problem that we're going to be addressing today is number 1, where does that line come from?
I like the best fit line being multidimensional already.
What do you mean?
You don't have a best fit line for females versus males. You just have one best fit line across height and weight.
Well, I did actually have best fit lines for the different ones, and then I can show you my Python scripts that I used to generate these. I started getting I started painting. I spent, I don't know, 2 or 3 hours what we would call painting the bike shed, and then I eventually gave up and like started a new script, and the comment at the top, it says, weirdly, when my goal is to actually get work done and not to, optimize my future work, I have no patience whatsoever for any of that.
Nice.
Because it's just like, no, I just want the program to go. I don't care.
Yeah. See, that's the mode that I tend to try to be in a lot when I'm in product mode.
Yes, it's the mode that you were in when you were productive. Anyway, so how is that line computed? How do we know that the fit is best? What does it mean for the fit to be best? And also, is the line good or bad?
You have to throw one of those in every time.
Well, nobody knows the thing is, nobody knows the answer to these questions, right? Best not to ask them, but according to big data, the best fit line comes from np.polyfit in the special case when the degree parameter is equal to 1. But unfortunately, nobody except big data knows what NP is beyond the fact that it's what you get when you import NP.
You literally mean this method is what it means. Just don't look.
So that leads a dead end. So what we're going to do in this stream is we're going to pretend that we're going to do some role playing. We're going to pretend that we're people from 2009, and we're going to think by hand instead of having big data do it for us. While I was doing this, I started breaking out a physical book. This is Norman Wildberger's book.
Oh,
yeah, I think it's out of print. It definitely smells like a book that's out of print. Yeah, I got it used. You know how like old books that go ahead, Mike.
Do you like measure the distance between the line and the dots? Is that how you?
Well, dude.
Kind of
like yeah, obviously, but like
define like
we'll get there.
Go ahead.
Well, yeah. So I mean, yes, basically. So like, what it is you're trying to minimize the deviation between the points and the line. Now, there's a couple different ways that you can do that. Now, I totally knew about this before I started doing this lecture, and I did not learn this from big data while I was having it critique my lecture. That actually there are two different things that are very closely related that I had confused with each other. And I knew that before I started writing this. I want to emphasize that. So this best fit line is, so one thing I learned, the biggest takeaway that I learned writing this was that statistics is all about what assumptions you throw into your model. So you're assuming the real world behaves in XYZ manner, and so we are going to build that assumption into our mathematical model. It's very much about making assumptions about the real world and then coming up with a model based on those assumptions. So the way that I assumed that this worked is like a very basic technique in large data analytics. And what I wanted to talk about eventually was that I want to get to, definitely not in this stream, but down the line, is like how IQ scores work, because we talk about things like IQ or Big Five personality and whatever. And I wanted to, in my head, it's a very simple picture how these things work. Basically, what it is I was thinking you draw this best fit line, and then what you do is you rotate your coordinate system so that this best fit line is like the x-axis, right? And then like the perpendicular line is the y-axis, and then you just project every point down to you project every data point down to its closest point on the line. And that, what was I going to say? That, if you normalize so that the mean is 100 and the standard deviation is 15, that's, that's your IQ score if you were to do this in higher dimensions. That's the correct notion, almost. There's a subtle thing, though, which is that what I just described is about minimizing the orthogonal distance between a point and the line, right? So you take this point here, and the closest point on the line is like over here. I don't know if you can see my cursor, right?
Mhm.
But what this best fit line is for is you are saying we're assuming that weight is a function of height, and so we are coming up with the linear equation that minimizes the error. It's only minimizing the y distance, not the x squared plus y squared distance. It's only minimizing the y squared because it's minimizing the error in predicted weight given the height. So there's like all these little subtle things in statistics that have to do with what assumptions you're making. So the best fit line, what np.polyfit is doing is, assume that the y-axis is a function of whatever variable is on the x-axis.
Would you get the same line if you reverse those two? If you assumed x was a function of y? I'm curious because like there's this other way of which, like, if we were going to try to run like a segmented sequence with back propagating the correction as we encounter dots going forward, and say what's our average minimum distance, and like populate, it would start kind of in the middle and like populate out both ways. I don't think we get quite the same line. Maybe, I don't know. I'm curious.
If you're with SVD, the technique that I told you to write in the description, the SVD is symmetrical. So it's going, it doesn't assume one is a function of the other. It just finds the line that what it does is it finds the line such that when you project the data onto the line, using the, orthogonal projection, when you project the data onto the line, the resulting data, projected onto the line has the maximum amount of variance. So what you're doing is you're finding the dimension in your data such that when you eliminate that dimension, you eliminate the largest amount of variance in your data. Does that make sense? It's kind of like how
minimize the amount of.
Okay, it's sort of like how when you are like designing a network protocol, you put the things that do the most amount of disambiguation first, right? Because that removes the largest amount of uncertainty.
Right.
You want to do that immediately. So that's kind of what this SVD thing is doing, is that it's basically saying, okay, what is the dimension of the data such that when I can either project down to the data and just look at that dimension, or I could do the opposite thing, which is eliminate this dimension and look at the sort of complementary space. And what is the dimension such that when I, look only at the complementary space, do I have the least amount of variance remaining? That's kind of the idea of SVD. Now, what least squares is doing, or np.polyfit, which we don't know how that works and nobody does. What that is doing is like saying, like I said, it's saying, oh, weight is we're going to assume weight is a deterministic linear function of height. Now, of course,
by the way, SVD is singular value decomposition. I don't know that we said that in words yet on the stream.
Well, everyone knows in the large data world what SVD is, Craig. You don't need to say that.
Some people think it's a rifle, though. So.
Oh, it does sound like like an old Soviet rifle from like.
It's the AK for when they're way over there.
Right. The AK-15.
I'm not going to make a joke that just came to mind.
Anyway, so we're going to think by hand. So first thing we're going to do is we're going to change our problem a little bit, and we're going to collapse out the non-essential detail. So the first thing we're going to do, just to kind of get rid of accounting overhead, is recenter our data so that the center of mass, the mean XY coordinate, is at 0, 0. Because having to do a bunch of subtraction, find the line, and then re-adding That's just really annoying. So we're just going to ignore that. And again, it seems like a fair assumption. It's an assumption, but a fair assumption that, our best fit line should pass through the center of mass of the data. Now, got to check that. That is true. That's true in both models, by the way. That's true both with least squares and with SVD. And we're going to drop the male-female separation because it was kind of cool to see, oh, okay, the women are smaller than gender 1 is smaller than gender 0. We can't make assumptions. But for what I'm trying to talk about, yeah. Sorry, Mike. All that matters for the purposes of what we're doing is that we have, two-dimensional data that kind of has a linear relationship. And I mean non-essential in a very, very literal sense of the word. So we're going to trim our problem so that we can focus on the essence of the problem, which is what is the best fit line and how is it computed? And whatever detail there is that distracts our attention from this, that's a distraction. We're going to eliminate it. And of course, my idea is, it's pretty easy to deal with accounting overhead once you have a pretty strong command of the essence of something. If you have a picture in your head of what's going on, then all the nonsense, you can just deal with that. You can split that in your brain into nonsense and the basic shape of the problem. But if you're trying to learn, the last thing you need is a bunch of nonsense. So yeah, like I said, statistics is the art of, at least so far, it's the art of making tasteful assumptions. There's that phrase, all models are wrong, but some are useful. And that's mostly about taste, which is weird coming from the math world. Math is very heavily about taste, but we don't talk about that. So here's our new data visualized. So our X and Y axes now are, what are you laughing at?
I'm laughing because it starts with the thing I was just saying, what if we start in the middle and sequence out?
All I did was compute.
Averages?
What the mean of height is and what the mean of weight is.
Right, and put that in the middle.
Yes. And then our best fit line goes through the middle. Because that would be really weird if our best fit line didn't go through the center of mass. Just mathematically, that should tell you something is really weird if that's not true. So side quest, we're going to have a refresher on some geometry that you learned in elementary school, right? You guys learned linear algebra, right, in elementary school. Great, and you've all watched Wildberger extensively, as all of us have, right?
A little bit.
Well, yeah. So, but for people in the audience who don't know, Norman Wildberger, where's that camera? This is his book. It's called Divine Proportions. He's this very weird heterodox mathematician. I'm a big fan of his. He's got a very, very weird perspective on math, and it's hard to explain to most people that there is even such a thing as heterodox mathematicians, but there is, and he is one of them. He invented, and that's what this book is about, basically a version of trigonometry that does not involve the use of angles. And it is much more mathematically elegant, and it's much more pleasant to deal with because it's purely algebraic. However, it's a lot less visually intuitive, I will say that. Once you get a handle on it, and if you're if you're somebody who has a lot of experience with mathematics, it's a lot more pleasant. But I'm trying to think of an analogy, trying to think, it's kind of like drinking black coffee maybe, or like drinking hard liquor, where Yeah, but no. If like somebody's first experience with alcohol is we're gonna do shots of of scotch, and like it's gonna be cheap $10 scotch,
Shots of
then
white rum.
right, or shots of like bottom shelf vodka, then that's not going to be fun, or drinking vodka directly out of the bottle. But like
The parts cleaner with
if you,
the aviators.
but like if you go to the liquor store enough, eventually homeless people who don't have IDs will ask you to buy alcohol for them, and they'll give you a bunch of money, and they're the most experienced drinkers on the planet, and they always want bottom shelf vodka, right? So like it's an experience thing, right?
I had a guy ask me to give him gasoline.
Anyway, no, gasoline's way too expensive, dude.
Well, right, maybe right now. they switch back to alcohol because it's finally cheaper.
No, dude, they literally in the U.S. they literally put ethanol. They dilute the gas with ethanol just to make it cheaper.
In Australia, well, no, there was like a green mandate for that in the US. You had to have 15% or something. In Australia, they had a problem with they were certain areas like close to the interesting people areas would ban alcohol like on the weekend or whatever because it had such a big alcoholism problem. And so they realized like, oh, we can get messed up on gasoline too. So they started drinking gas, and then they started adding this like bitter, like awful tasting bitter chemical to it so that it was like gross to taste gasoline, and it just didn't stop them at all.
Nope, that's not going to do anything.
Nope. So
that's
what I learned about Australia when I was stuck in Darwin doing a training exercise. I'm like, oh, this is worse than I thought. The memes are real.
Yeah, it's bad. Anyway, so quadrants. So quadrants is normally you call it distance, but quadrants is distance squared. And mathematically, quadrants is kind of if you read like Euclid, which I need to get back into reading Euclid. His when he talks about what we would call distance, he very much focuses on, well, draw a square with this side. So if you've never seen Mike,
can you explain to me the purpose behind defining distance squared as a thing?
So it's more that distance is defined as the square root of quadrants, but distance is okay.
Oh, because the formula for the distance in a coordinate system is that. Oh, okay, no, that makes sense.
Yeah. So this is a thing, and when you get advanced enough in any subject, you have this issue where the basic ideas in every subject, they very much come from our intuitions as apes. So like Leonard Susskind has this wonderful, wonderful lecture that it's like a Stanford lecture that he gave to the public, and it's about basics of quantum mechanics, and he's like, as animals we have all of these intuitions about nature, and these intuitions about space, and these intuitions about physics, and they are correct given our size. And when you get really, really big, when you start talking about really, really big things like the size of the solar system or bigger, or if you start talking about really, really, really small things, the size of a handful of atoms, those intuitions are just not correct anymore, and you have to abandon them, and you have to just look at what the evidence tells you on its own terms. So when you get advanced enough in physics, you have to sort of abandon your ideas about causality and about how time works and how space works. And when you get kind of deep enough into mathematics, you kind of have to realize that it's like, okay, dealing with all these square roots are nasty. If you can just not deal with them, it's better. So, if you've never seen this is a wonderful, nice little elegant proof. I don't want to call it a proof, but a proof of the Pythagorean theorem. So you have two squares here in green. You have a squared and you have b squared, and then you have these little triangles here. Now you can take this triangle over here and slide it over. You take this triangle, you slide it down. You take this triangle, you slide it up, and you leave that triangle there. And now you have a square in the middle that where all the sides are C, and you have done nothing that modified the area. Now, there's a lot of assumptions that are baked into this picture. And this is why I put proof in quotes, is that this is not really a proof, because like the biggest assumption is that moving a shape doesn't change its area. And that's actually a really, really big assumption. And in almost all, that's only true in a a narrow subset of possible geometries. In general, when you move something, its area changes.
Well, that's definitely true in relativity.
Yes, yeah. And that's the general thing, right? So the square root of the quadrants is the Pythagorean distance, or the crow flying distance. So you have a point like this is a bad example. Whatever, you get the point. You take x squared plus y squared, and you square root that, and that's the distance from the origin to that point. So the inner product,
right? Because you're looking for c.
Yes. So you take a squared plus b squared, and the square root of that is c. But really, you should just take a squared and b plus b squared, and that's going to equal c squared, and you should just leave it as is. That's what quadrants is.
So don't go back. Don't do the root part.
Don't do the root, because your idea that everything should be based around distance is an intuition you have as an ape. And as a mathematician, we have to work with big data. Big data is smarter than us, and big data doesn't care about distance.
Right. Well, it's kind of like when someone asks me where in space should they visualize that a PID lives at. It's like, ooh, that's an interesting question.
Ooh.
And it's the wrong shape of question, but that was in the context of me explaining the relativistic effects that I got from having bots run characters through a mud at max speed, at the message max, and that you got that time slowdown thing.
Right.
So where is he going? Like that gets into like simulation theory questions.
Are you familiar with this thing in distributed systems where you get relativistic effects? I don't know if he can hear us.
Let me see if this.
Anyway, there's a thing where
I can hear you.
Okay. So relativity is basically this set of effects that emerges when you have basically a speed at which information travels that's pretty slow, and like the speed that it's slow enough that you can perceive it.
Well, it's fixed. The speed winds up being a consequence of.
Yeah, but you get the same thing like I'm trying to think, like the War of 1812. Like the whole way that started was like Britain basically sent America like I'm going to screw up my history here, but my memory is that like Britain sent America, oh, hey, you know what? Never mind. Let's cool it. Let's chill out. We don't need to go to war. And America didn't want to go to war, but they're like, well, we have to strike first. So they sent a declaration of war. And then, messages are on the way.
There was no three-way handshake going on.
Yeah, there wasn't. And so they got the peace message back, and they're like, God damn it. Okay, I guess we got to go to war.
Row faster.
Yeah. So that's the sort of thing that happens in relativity, is that you have to think about, you'll have different people have different notions of the sequence at which events occur. So you can't assume you can assume that each individual party has a fixed view of the sequence of events, but you cannot assume that is common across different parties.
It's amazing how central that is to distributed game design, and it's simultaneously how few game designers are willing to deal with the problem.
It's very freeing once you accept it.
Mm-hmm.
Yeah, but it's hard
The
to
time
accept.
is fake, but observed sequence is real.
Yes, time is fake except for me.
Mhm. That's a good
Anyway.
summary, actually.
Yeah. The dot product, I'm sure you've encountered this. You've done some game programming. So you have two vectors and
We
you
rarely use academic math terms, though, surprisingly.
yeah, what do you call this?
We would just say, like, I would just write the formula there, and that's it. There's no.
What would you
we don't
call the
it-
function? You would call it stupid thing?
No, that would be buried inside of something larger usually.
Anyway, but you just take, each coordinate, you multiply x times x and y times y, and you add them together. In physics and engineering contexts,
but like the way you've written, that's not the way you'd write it actually in a program.
Right, you would write it as like a for loop, or as like some sort of weird.
Well, I mean, that's not like a function. Like you've got IPAB.
Oh yeah.
Equals.
Well, this is an equals.
Stuff.
This is an identity, right? It's not a function, correct?
That's what I mean. It's like that's not some code that runs.
Right. So the inner product of A and B in physics, they would call it the magnitude of A times the magnitude of B, so the length of the vector, times the cosine of the angle between them. So I think this is the law of cosines, but I was too lazy to look it up. So if you forgot, if you have an angle, so this is the angle from the positive x direction, the cosine is the x coordinate. So if like you take the angle and you were to look at the point on the unit circle that corresponds to that angle, the cosine is the x coordinate. So the physics view is helpful when you focus on the special case where A and B are both points on the unit circle, so their magnitudes are both 1. So important special cases, the inner product of a vector with itself is its quadrants, right? So x1 times x1 plus y1 times y1, right?
You're asking like, what would I call this in a game program? It's like, that'd be like diff or delta or plot or something, but it wouldn't be these words.
Yeah, well, that's why we're here.
Yeah, right.
So the inner product of a vector with minus itself is minus its quadrants. So again, magnitude of A times magnitude of A. If you take x and minus x here, the cosine is -1. So there you go. The inner product between two vectors is 0 precisely when they're orthogonal. So that's, again, if you have x and y, so the angle here is 90 degrees,
right,
then the x coordinate is 0. So,
but that correlates just to slope in this case, right? Essentially.
I don't understand your question.
You've got the yeah, so cosine 1 is like always 45 degrees because you're the slope of the angle that you get. Like you as you extend the angle, as you extend the sloped line going towards a radius, you're gaining 1 as you move 1.
Let me clarify. You pick the angle, and you pick the point that is on the circle, such that when you draw this line, it forms that angle. So the cosine is the value of x, assuming that the point is on the unit circle. So it's not like this point here. It's specifically this one up here.
Right, but cosine 1 corresponds.
Would be like here.
Okay.
Cosine of t is this angle here. It's not the hypotenuse here. It's the angle. What are you talking about? Oh, cosine equals 1. I'm sorry. I was confused. I thought you meant cosine of 1, and I'm like, why would
No, cosine equals 1 is...
Yes.
a specific slope that also happens to be 1.
That slope would be 0.
If it's 1, okay. But you say when the inner product between two vectors is 0, precisely when they're orthogonal, which is like
Yeah, here.
straight up and down.
Yeah, here I might have a GeoGebra down here somewhere. I don't have one where I have the cosine.
It's okay. We can.
But
mess with it later.
basically, okay, the cosine. Yeah, so this is the sort of thing where I was saying you gotta be aggressive about asking questions, because I forget that, like, I just spent years and years and years and years of my life dealing with cosine, and so I just, like, it's just burned into my brain, every little thing about cosine, and so, like, I
only have ever cared about trigonometry insofar as it's really good at helping me like plot things.
Okay. Let me maybe. I know I have a GeoGebra of this somewhere. Let me try to find it. It's not here. I have on my other account. Let me just search for cosine. Okay. Here, I just found this on the internet.
So cosine of
Yeah,
the angle
so
0.
So
0.
the cosine,
Yeah.
yeah, cosine of the angle 0 would be 1. Is this big enough?
Okay. What's 90 degrees in this one?
For 90 degrees.
Oh, 0 is oriented to the right. Ah, okay, right. Okay.
Okay. That might
And
have
you're
been
back.
the confusion.
Yeah, I'm mixed up in orientation, but okay. Well, and all of these. Okay.
Yeah, here, let me put this in the Discord so that I remember later. Here. There we go. If you want to play with that.
Out of curiosity, if you could answer this briefly, I don't want to like derail the whole stream, but why is it the case that calculation of the like trigonometric functions tend to be established by, at least when I was a kid, they were established by table. I even say that in software, it's still established by tables, and we bake that straight into like hardware these days. So so programmers like me just cheat, and we like look up whatever the formula is to get what we want plotted, and we just use that and go whatever. But internally, like inside of like hardware and a lot of software systems, there's just a big table of like really gnarly, as refined as they could get for the resolution that the system can provide, table of pre-computed sine, cosine, tangent. Like, what's hard about deriving them? Is it all square rooty mess?
So the way that sine and so the formal definition of sine and cosine. Here, let me see if I could pull it up.
It's like I don't even remember from school, and I actually use this in work sometimes, but like I don't remember trigonometry in depth.
Ooh, I might be able to actually. Let me look it up. Just see. So here's an interesting thing. So this is actually a great visual. I forgot that you can just go on geogebra.org and just search for things, and somebody will have an animation. Yeah, right. People have just made them. So this is how cosine is actually defined. This is like the definition of cosine. And it's an infinitely long polynomial.
Okay.
And each additional marginal term only gets you a tiny, 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 tiny little bit of convergence. And it's these like really, really harshly diminishing returns. So this is with 0 terms,
Okay.
is that it's approximated as the function y equals 1. Okay, if I add 1, if I add 1, now we have a parabola. So it's minus x squared, basically, plus 1. Then I add 2, and it's an x to the 4th. I add 3,
Oh.
and 4, 5,
Okay,
6,
that does suck.
7, 8, 9. You can see that I'm really not gaining a lot here. I'm up to 29 here.
Mm-hmm.
Yeah. Now, thankfully, it's a periodic function, but
Right.
its period is pi, or it's 2 pi. So with degrees, it's not that bad because like computers can divide by 360. It's not that bad, but dividing by 2 pi is going to be a challenge for a computer. They struggle with dividing by 3. So, so what Wildberger focuses on, and this is why I like Wildberger, is he focuses on this quantity called the cross. Now the cross, I did this for you, Craig, is I wrote it as divide the square of the inner product by multiplying the quadrants of A times the quadrants of B, right?
Oh,
See, I even put the arrow there to tell you this is a definition.
you did. It's all functioning now.
Yeah, so the cross is just the cosine squared. Cosine always ranges between -1 and 1, and so the cross always ranges between 0 and 1. So it's useful to think of the cosine as measuring the similarity of two vectors with respect to their direction. So like the cosine of the angle.
Wait, the cross is... Oh, that's cool. Okay.
Yeah, it's just the inner product squared divided by the product of the lengths. So when the directions are the same, the cosine is 1. It's 0 when the directions are orthogonal. Right, it's the directional similarity. So when they're orthogonal, they have 0 directional similarity. And when they're like opposed to each other, they have negative directional similarity. That would be a way to think about it. And what the cross is measuring is it's measuring the similarity of lines. So it's almost the same notion as the direction of the vectors, but the lines collapse the distinction between forward and backward. Does that make sense?
But the lines collapse.
Because you're squaring it, so the -1 becomes
right,
1.
Right, okay. Right.
So if we want to be pedantic, the cross measures the similarity of pencils, where a pencil is like you pick a line and every line, that line and every line that's parallel to it is that pencil of that line.
Okay.
So like here, I have a here. Okay, this is a pencil. This is a subset of the pencil. But this is like, it's this line and every line that's parallel to it.
It could be right.
Okay, so it's measuring the similarity of two pencils. If you want to be pedantic, which we don't because this is exposition. So the cross measures the directional similarity between lines insofar as it is 1 precisely when the two lines are parallel and it's 0 precisely when they're orthogonal. So again, ground yourself, it's just the dot product. You square it, you normalize it by the lengths of the vectors. It's capturing the same basic notion. It's roughly, is it parallel or perpendicular? But it's collapsing out all the accounting details having to do with, absolute direction and what size the vector is. No, we're not doing any of that, right? So in physics terms, what Wildberger is doing is he's starting with the physics notion, the law of cosines, and then you square both sides, right? So you take this becomes quadrants of A, this becomes quadrants of B, and the cosine becomes the cross, and then you divide out the quadrances, so then you get the square of the inner product divided by the product of the quadrances, and that's the definition of the cross. So the cross is useful for our purposes because it's purely algebraic. So just concretely, that means you can compute it without resorting to approximation or floating point arithmetic. It also means that when we're doing cryptography and we want to do like geometry with modular arithmetic, that all of the geometry that works in Euclidean space, it works perfectly with no modification in modular world, which is definitely not true of, sines and cosines. Those have no analogy.
That's interesting.
But you can take, it also works perfectly well with no modification in curved spaces. So in like hyperbolic or spherical spaces. Like there's more
Really?
terms that pop
Okay.
out. But like if you take the generalization that in two-dimensional Euclidean space produces these formulas, and you apply that generalization to a sphere or a hyperbolic space, it's really just not a big deal at all. It's actually really, really pleasant to work with, and it's way more pleasant than, it's really, this is why I'm like, okay, yeah, I guess I'm friends with you, so I'm not allergic to people who are called kooks, because yeah,
Am I
but like,
kooky?
but like my thing is I just listen to you and I'm like, okay, well, do you make sense and are you usually right? Okay, that matters a lot more than do other people think you're right? No, are you right?
Yeah.
Um,
Yeah, that's the kind of folks that we hang out with too.
Right.
That's really interesting. So this should be also much easier for machine computation.
Correct. Yes. Which is why
Like
Jarvis
tremendously.
and I both love Wildberger, is because we were trying to, we both didn't like pure math because it was so kind of loose logically. And the only thing that we could sort of make sense of was when we would write it as code. And we loved Wildberger because we could take his work, we could take his sort of formalizations of this math, and he would explain it in a way where you could go write a program that did it.
And it's not fuzzy.
It's not fuzzy. It would give you the exact answer. And it would work in modular arithmetic. So when we're, going to be talking about.
But this is why it works in modular arithmetic, is that you have this exact.
Because
you have an exact
algebra. It's just multiplication, division, squaring things, and then like sometimes you'll have some quantity that is defined as the solution to a polynomial. So it might be very, very difficult to find the solutions, but that's still a definition that's a lot easier to work with than, an infinite series. Well, we just don't have the notion of an infinite series when we're talking about an elliptic curve in a prime field. That's just not a notion that we have. There's no concept of approximation. That's the whole point of cryptography, is that if you're wrong even a little bit, it doesn't work at all.
Right.
That's why cryptography works. So that's one thing that like it makes cryptography really, really, really pleasant to deal with. It's really, really nice. It's some of the most beautiful and like really clean mathematics you'll ever deal with, because there is no tolerance for being like wrong a little bit. There's no fuzziness whatsoever. Everything has to be exact and like perfectly accounted for.
Doesn't that get a little weird when you get into like homeomorphic hashing functions?
I mean, I don't think so.
Okay.
I mean,
I'm thinking through in my head too, like about sort of fuzzy, like image similarity algorithms, but those also. I mean, you do wind up getting down. You have a clear scale, and at scale X, you get a yes or no.
Well, homeomorphic hashing, or no, it's homomorphic hashing generally, not homeomorphic. Homomorphic hashing.
I may have misspoke. Sorry.
Generally, I'm going to screw it up, but so homomorphic, it just means it preserves structure. So homo, same, morphic, shape. So it preserves some sort of structure. What we're talking about in a minute here are called linear homomorphisms. So that's just a general term in mathematics. the structures that it preserves are discrete structures. So it would be something like, okay, so like for instance, we go down here and I expose this like long algebraic identity. Where is it? And basically the bottom line is that with complex numbers, so you know about complex numbers, is that if you take the length of the product of two complex numbers, it's the same as the product of the length. So you can take the length first, or the quadrants, make the quadrants first and then multiply the quadrances, or you can multiply the two complex numbers and take the quadrants, and you get the same result in both cases. That's an example of a homeomorphism, or of a homomorphic relationship, where it preserves this structure.
Right. Okay.
Okay, so that's the sort of thing that homomorphic hashing does, is where there is some, so like it's still
That looked
opaque.
really polynomial adjacent too, though.
Yeah, but where it's opaque, but at the same time, what I can do is I can say, let me just give you a really basic example that, like, this is a hypothetical example. I don't think this is a real example. But like I have this piece of data and I have this piece of data and I have, so I have data A and data B and I have C, which is just the bitwise XOR of A and B. And I hash A and I hash B and their hashes look totally crazy. And I go hash C, and a homomorphic hash might have the property that so C is the XOR of A and B, but the hash of C will also be the XOR of the hash of A and the hash of B. That's the sort of thing that would happen with homomorphic hashing.
That's wild.
Yeah, it's very, very, very useful. It's an incredibly useful tool.
Also feels like some kind of like trapdoor space lives there.
Yeah. It is way out on the edge of okay, so the thing is, like, AI keeps finding all of these bugs in, like, pretty serious security bugs in software, right? And okay, now the reason that it's finding bugs is because the bugs are really easy to find. It's just nobody's bothered to look for them. Or, the people who have work for the NSA and they don't disclose them. And it's just because programmers are like really bad at their job. Or like what I read from somebody who, was a contributor to Nginx was like, we had known about all these security bugs for a long time, and we were just like, okay, we just like the ROI of trying to talk about them in public isn't going to go anywhere because they're all in these subsets of Nginx, these features that nobody uses. And because nobody uses them, nobody's interested in fixing problems there. And so, like, who cares? And so, like, that's the thing that Mythos is. Those are the sorts of bugs that Mythos is finding. But like, domain experts knew about them. Like, and it's not universally true, but like, that's generally what's happening. It's just programmers are really bad at our jobs, as we all know. Yeah. So let's see. Okay. So we get it. Cross is cosine squared. What was I going to say? Yeah, so square both sides, notionally. Right.
Cross is cosine squared, but the reason it's cosine squared is the interesting thing. I'm just going to have to play with that to like fully appreciate it, but that's really neat.
So notionally, it means that the cross is much more amenable to the use of high school algebra to connect concrete logic with visualizations. So algebra is generally a lot more portable than non-algebra. That was what I was talking about. So you can use it to do cryptography, for instance. It's a much more powerful tool to be able to precisely relate things to other things, which is what math is about. Most people who remember trig only remember this identity, which is sine squared plus cosine squared is equal to 1.
That's me.
Yeah, but that's the most important one. And all it is just the Pythagorean theorem.
Right.
Sine squared and cosine squared. You square the x coordinate, you square the y coordinate, it's equal to 1 squared, which is 1. So the cross is cosine squared, and the complementary sine squared quantity is called the spread. So the spread between two vectors, it is x1 times y2. So we have x1, y1, and x2, y2. It's x1, y2 minus x2, y1. You square that, and then you divide by the product of the quadrances. So that inner quantity that's in there, that's called the twist, or it's also called the determinant. Visually, the way to think about it is the signed area of the parallelogram that's spanned by the two vectors. So you have these two vectors here.
I'm sorry. The inner quantity. I'm trying to like pin down. Inner quantity.
So this.
It's called the twist or determinant. Okay. The twist and the determinant are the same idea.
Yeah, aka the determinant. It's called the determinant everywhere, but Wildberger, I found it in his book, and it's called the twist.
Okay.
That's what he calls it, but it's called the determinant.
I wonder why he came up with that.
He comes up with weird names for everything.
Well, but I mean, he has like a reason for that that's not always obvious at first.
Oh, yeah. He always has a reason.
Mm-hmm.
Probably because it generalizes to a slightly different thing, and it agrees with the determinant in this one case.
The signed area of... We went over this a little bit when we were doing like circuits before too.
Yeah, I was going to bring up circuit stuff here.
Okay.
But I didn't want to get into scope creep. But if you want, I can talk about that in the future.
Actually, like if you did a short one that's just like, why can area be signed? That might be fun. Is like a short.
Oh,
discussion.
that would be a good.
Because that was a cool idea, but it didn't like.
Yeah.
It wasn't. It was one of those things that like lingered in my mind while we were going through the discussion, and then like halfway through another part, it dawned on me, and I'm like, whoa! And I kind of wish I could have just focused on that question.
Yeah. So there's that would be actually a useful thing. So one cool thing that you can do. So you have this parallelogram here. Here, I might have it. Why do I keep closing my window where I oh, it's on the other.
I can make passive aggressive catty comments about why you close windows.
See. Yeah, here we are. Yeah, so you take these 2 points, and so we talked about how the determinant is the area of this parallelogram, but if you divide it in 2, you can think of it as like the signed area of a side, right? So like it's giving you the area of this perspective triangle, right?
Perspective triangle.
Right, so you're looking at the origin and you're looking at this side. And so I see A and B, and then this is my field of vision here, right? What is the area of that field of vision?
Right, okay.
Okay, now, if you take an arbitrary polygon, you can, from the perspective of the origin, you can just triangulate it. So you can look at like A to B, and then B to C, and then C to D, then D to E, E to F, F to G, and then back. Right? If you take because there's a sign, and the sign switches when you, I should include this one. Here, I'm going to bookmark that and bookmark that. Because there's a sign, the negative areas cancel. Oh, I haven't installed AdBlock yet, apparently.
Hey, you can get some ole, the football way.
No, dude, I accidentally clicked.
Available at Walmart.
Dude,
it's
I
like
was
America.
going on GeoGebra and I was searching for something using this search function, and the first one I clicked on was some dude in like Brazil or Mexico or something, and now GeoGebra is like convinced that my language is Spanish, and I don't know how to change it. So información.
Yeah.
This
Oh,
hours
yeah. You're
ago,
right.
yeah, everything's in Spanish. I don't.
It's okay, dude. Grok thought that I was an inquisitor from 40K for like 3 months, and it would not get off of that. And so every time I ask it a question, it's like the heretics demand that. And it's like, whoa.
And it's like, dude, I just wanted to know like what the syntax for lists : fold L is. I can't remember the argument order, dude.
Yeah, or like I was trying to remember like the name of like fish in English because I don't know English fish names, and it's like in the I forgot what it's like in the something that in the Terran region of the Imperium, blah blah blah, and it's like whoa, and then like it would tell me a fish name.
Okay, so let's just suppose we want to take this little rectangle here. Okay, we want to measure the area of that rectangle, right?
Mhm.
So first thing we're gonna do, we need to pick an orientation that agrees. So we're gonna go here. So here, the signed area is -1, roughly.
Mhm.
Okay. Then we're gonna go from there to there. So now the signed area is 0.93 apparently. Next one is from here to here. That's this signed area. Then this one is going to be 0. Right?
Mhm.
So what we end up doing is every portion of this gets, basically the double counting cancels out with the negative counting. And the areas that you're not supposed to take the area of, they get subtracted out. And so this is a way you can take areas of arbitrary polygons. It's maybe not very efficient. It involves a ton of multiplication, but
multiplication is when it comes to machine computation, that's actually fine though.
Yeah, I don't think there's a lot of division. So yeah, that's fine. So anyway, notionally, the spread is the separation between lines, just as the quadrants is the separation between points. And in rational trigonometry, spread plays roughly the roles that angles do, or the role that angles do in irrational trigonometry. So it's
right.
Angles are sort of separation, right? So to keep track of the rough analogies,
I love how you're able to say irrational trigonometry though. Like
dude,
outside of mathematics.
Dude, so much math terminology is just propaganda that's stuck. Like real numbers and imaginary numbers, that was literally just fucking propaganda.
Well, I like how real numbers
are fake and imaginary numbers are real.
Yes. Yeah. Like that's a concrete truth. And you try
and it's like, and so like, I sometimes I'll be learning something about, some other field, and like somebody will panic and they'll be like, okay, no, you can't take this term at face value. You have to understand. And I'm like, brother, you have no idea. You have no idea what my field is like. It's just all propaganda.
Well, but that's not a commonly known thing. How wrapped up in weirdness. Well, like you were telling me about, I was like, well, at least mathematics will be isolated from like sort of the woke scourge. And like, no, man, it's like wide open.
No, it's gonna be the worst of the worst because math is like
the crazy people just aren't skilled enough in that to know how to subvert it yet, but it's wide open.
No, the crazy people are extremely skilled in math. Have you heard of Rust?
Yep. What I mean is like there's not there's not the same cabal. There's not the same cabal of like PhDs trying to like undermine math yet that has happened in like a lot of the humanities.
Not yet. It's not.
It's forming though.
Like there's
the vanguard is on the march.
There's no Judith Butler in math, but also mathematicians are unaware that there are Judith Butlers on the rise.
Yeah. Like it's a coming thing for sure.
Right. So anyway, to keep track of the analogies, cosine squares to the cross, and the dot product, when we do that, when we square it and divide it by the product of the quadrances, it normalizes to the cross.
Mm-hmm.
Sine squares to the spread. the determinant, you square it, you divide by the products, that normalizes to the spread. So
I
just
like
keep-
these definitions much better than the ones I had seen previously. That's a really great.
Yeah, I like just keeping track, because I'm throwing a lot of terms at you, and just keep in mind kind of these are the, okay, this kind of is the direction that things flow. This is the direction that things flow. And in particular, when you go this way, you lose information, right? When you square, you lose information.
Right.
So it's okay. So much in the way that the dot product captures the raw similarity between two vectors, the determinant captures the raw independence between the two vectors. Okay, so this is a technical term. The notion of linear independence is like extremely, extremely, extremely important. But in its full generality, it only makes sense in 3 dimensions or higher. In 2 dimensions, it's kind of a trivial concept. So the determinant also generalizes to volume measurements in higher dimensions, but it requires 3 vectors in 3 dimensions, 4 in 4 dimensions, 5 in 5, etc. So bottom lines, you take any finite set of non-zero vectors, v1 to vn. They are called linearly dependent, and it doesn't matter which one you pick. You can pick any one of them. The order doesn't matter. I just picked the first one because it was easier for notation.
Mhm.
It's this set of vectors is called linearly dependent if one of them is a weighted sum of the others. So if v1 is in the span, so the span is the set of weighted sums, but they're called linear combinations is the formal term, but it's a weighted
Okay.
sum. So the
It's
set
a weighted
of
sum of all of them.
right. So 3 times s2. So like, let me just give you a very concrete example. So you have the coordinate 3, 4. That is
Okay.
3 times 1, 0 plus 4 times 0, 1. Right?
Hang on.
Yeah. So here.
Say that again.
So, okay. I'm just going to pick this. Okay, I'm actually going to go to 3, 4, just so that you can see what I'm talking about.
Mm-hmm.
Okay. Oh, apparently
It's close enough.
okay.
Oh, there you go.
So this vector here
Mhm.
is 3 times this vector plus 4 times that vector. Is the vector sum of 3 times this vector and 4 times that vector.
Okay, okay.
Right. So
Yes.
these two vectors are linearly independent because
Mhm.
there is no way for me to write this vector as a weighted sum, but when you only have one, it's a constant
Mhm.
multiple. So that's why
Right.
it's trivial in 2 dimensions, right?
Okay.
Right. So if one of them is a weighted sum of the other, if none of them can be written as a weighted sum of the rest of them, then they are linearly independent. So in 2 dimensions, it's
Okay.
a trivial concept
Mhm.
because the only time you get linear dependence is when they are constant multiples of each other. But in 3 dimensions, that's where it starts becoming a non-trivial concept because you can have 2 vectors that span a plane, and you could have a third vector that could be on that plane.
Okay. And
Right.
oh,
So that's linear dependence. Linear independence is that third vector is off the plane.
is there a good way to identify that, Matt? Like,
Yes, there is. I am so glad you asked. So glad you asked, because that's bullet point number 4 here. Okay, in 2 dimensions, that just means the vectors are dependent if and only if they point in the same direction. One is a constant multiple of the other, and they're independent if they point in different directions, right? So in 3D, this means that the third vector is not in the plane spanned by the first 2. An equivalent statement is that a set of vectors is linearly independent if the only linear combination of them that equals the 0 vector is the trivial one where every coefficient is equal to 0. So algebraically, it's very, very trivial to see that this is true. So we have v1. So this is our condition for linear dependence, right? One of the vectors is in the span of the others. Okay, well, -1 times v1 blah, blah, blah. So, and then if you have 0 vector is some non-trivial linear combination of the others, then like you get the point. Does that make sense?
Mhm.
So in 2D, visualize that there is no linear combination of 1, 0 and 0, 1 that equals 0, 0. So there's no weighted sum of those two, except for the one where both coefficients are 0. In 3D, you have a plane that's spanned by v1 and v2. So you have two vectors. Let's say the x coordinate vector and the y coordinate vector. Those are called E1 and E2 and E3, by the way. They're called the standard basis. So 1, 0, 0 is E1, 0, 1, 0 is E2, 0, 0, 1 is E3.
Is that kind of arbitrary that we're using the value 1? I mean, could it be 2, 0, 0, 0, 2, 0, 0, 0, 2?
Oh, dude. Yes, but
I'm not saying we have to go all the way through that. I'm just sort of asking, is that essentially arbitrary?
Everything, okay. Yes,
I'm asking if there's some magical property of 1, of a component value 1.
Yes. Okay, here's the way to think about it. Imagine that you're doing like relativity, and you have
my intuition that led me to ask a question is that it's kind of like if we want to get some offset perspective, and we have to do it both directions.
Yep.
To have a perspective at all, right? Okay,
yes.
so does it matter for my vision if my eyes are wider or closer together? It kind of does, but it's essentially arbitrary.
So 1 means 1 from your perspective. And when you change, that 1 from your perspective might be 2 from somebody else's perspective. But from their perspective, that's 1. They have 1, and that might be a half from your perspective.
Right.
So right. So linear transformations are how you can relate these sort of scaling things. So we're about to get there. Okay. So
I'm sorry. I'm just kind of curious what they hear. Computationally speaking, is it easier to keep the values 1? Does that simplify?
Oh, yeah.
Like from the mechanic, like just again, this is going to a machine perspective. So this is a tooling question, not actually a math question. Would that actually help anything? Would it matter at all?
If you're doing modular arithmetic, no. If you were doing rational arithmetic, the problem with doing arithmetic with rational numbers is you have to use big nums, and those nums get really big really quickly.
Right.
And so the more things that can be 1 or 0 or, very clean values, the better.
Okay.
So, but with modular arithmetic,
at least try to start small.
Right. But with modular arithmetic, you have a fixed integer size. Your computer doesn't care. Your computer, you have a fixed number of bits. You have 64 bits. Your computer doesn't care if the first bit, a bunch of them are 0, or if there's a bunch of 1s there. It's the same.
Oh, well, then clearly we should just start with 0.3.
Well, we're talking about integers.
Joking.
We're talking about integers. Okay. Well, we could do 3/10 because we can do division in modular arithmetic, right? So anyway,
yeah, but
equivalent statement is that a set of vectors is, yes, I told you, it's linearly independent if the only linear combination of them that gives you the 0 vector is the trivial one where every coefficient is 0. In 3D, visualize that if you have two vectors that span a plane and you have a third vector that's in that plane, so we're talking about linear dependence here, the case of linear dependence, then it's possible to get back to 0 by simply using v1 and v2 to get to v3, and then minus v3 to get back to 0.
Then minus. Okay, right.
Exactly what I was just doing here. Okay. An equivalent statement is that the vectors are linearly independent precisely when the dimension of their span is equal to the number of vectors.
Wait, the vectors are linearly independent. Okay. Precisely when the dimension, what's the dimension of their span?
So meaning like, does it span a plane? Then it's 2 dimensions. If it spans 3 space, it's 3 dimensions.
Oh, okay, right.
Yeah, the dimension of their span is equal to the number of vectors. So if you have 3 vectors and you span
Okay.
and you look at their span and it's a plane, then they're dependent. And if you have
Okay,
2,
that makes
yeah,
sense.
yeah. An equivalent statement, yeah, is that the set of n vectors is linearly independent precisely when the determinant of the n vectors is non-zero.
An equivalent statement. Set of n vector, okay, is linearly independent precisely when the determinant of n vectors
Yeah,
is
so
non-zero.
let's just look in
Okay.
the 2-dimensional case.
Mhm.
Okay, this is 0 exactly when these two are collinear.
Okay.
Right, so these 2 vectors span a line. That's when the area of the parallelogram that they span is 0.
Is 0. Okay.
Is precisely when they span a line. If they span an actual, if they collectively will span the plane, then the determinant, then the area that they span is non-zero.
Okay. All right. Wait. So, okay, that makes sense now.
Yes, and in 3 dimensions, it's a volume.
In 3 dimensions, but yeah.
And you divide by the number of dimensions. So here you divide by 2, and I think in general with n dimensions, you divide by the factorial of the number of dimensions. So in 3 dimensions, you need to divide by 6, and then by 20, and then by by 24. I'm bad at math. Whatever 6 times 4 is.
It's funny how many mathematicians are bad at arithmetic.
Yeah. There's a joke about, I think it was John Nash. He was, proving some statement about prime numbers, and he's like, I don't know if it was John Nash, but it was some famous mathematician. He's giving this talk, and somebody asks, okay, can you give me an example with a prime? And he's like, okay, let's take 15.
That's perfect. No,
Yeah.
it's like go to dinner with a bunch of mathematicians, and when it comes time to split the bill, they'll ask me to do it. I'm like, what? Seriously?
Yeah, it's like, yeah. And I am, oh God, I'm actually going to do a video about this. Here I can give the story very briefly. So my wife got one of these candles from some liberal candle store, and she was burning
But it was cool.
and it smells good. It's actually a really nice candle. She's burning it, and like it has like a big radius, and so the like there was a big puddle in the middle, and it was starting to drown the wicks, and like it was starting to like get wax that wasn't melting like up on the sides of the side walls. And so like she asked me, she was like, hey, can you try to like melt the wax off the side walls so that like the candle doesn't get all fucked up? And I'm like, sure. So I went and got a blowtorch and tried to do that. And apparently candles do not have heat resistant glass. They do not come in heat resistant glass. So I broke. Yeah. See, I'm not crazy. Okay.
Well, but that's because it was a liberal candle store. If you went to a conservative candle store, the candles first would smell like diesel.
Freedom Candles and Surplus.
Yeah, Freedom Candles smell like diesel.
Yes. Yeah.
They'd be in like Pyrex or something. Or no, they just have steel cylinders.
Right. Yeah, it's steel. Right.
It's steel. So it doesn't look cool at all. You don't get any like glow in the room.
Right. But the candle never tips over.
Yeah. Oh, it's super stable. This is like survival candles.
Yes. Tactical Candle Company.
Tactical Candle Company. And they have like camo like
yeah.
We can put vents in it too. Powder. It looks like a suppressor. Just because
it comes in the shape of a shotgun shell.
Oh, dude, I would totally buy one of those.
I would buy that. Yeah. Anyway.
Oh, that's awesome.
We were talking about this where We were buying what was
Oh,
it?
you got
We were
this
buying
liberal
baby-
candle.
we were buying cat baby formula,
Mhm.
and we were in the pet store, and I just realized is like, oh, they had like, you know, they had the exact same product with two different packagings, and one of them was for the female customers, and one of them was for the male
Oh,
customers.
right. Yeah,
Right.
yeah.
And so like for the male customers, they have like this lion like ripping a gazelle's throat out, and it's like extreme kitten wilderness milk replacer. And then for the women, it's like this pink one, and it has baby written on it. It's all this flowery text. It's exactly the same product. The ingredients are exactly the same.
It's
But
like this kibble's for predators, and this like this one's for kitties.
tactical kitten milk.
Tactical predator kibble.
Right. I showed you about the tactical roofing torch at Tractor Supply, right?
Yes, that was like I kind of wanted one.
Yeah, I wanted one too, and I'm like, I don't. The problem is, I don't need a roofing torch.
Yeah, yeah, totally. Like
and it was like
I would never use it
$90.
for that. Yeah, I would
Right.
never use it for that. But like, I just want one because it there was something attractive to me about that.
Yes.
Like having a,
Anyway, so anyway, so like dealing with the candle, and my nephew and I were trying. Oh, so like I took the candle with me, and
that's why you need the roofing torch to melt the wax off of the tactical candle.
Well, that's
rim.
what I tried to do, dude, and that's why it broke. Because
That's because it was a liberal candle.
Well, yeah,
Jeez.
because they don't have heat-resistant glass on candles, which I was
That
just
is
like,
wild. I would have thought.
that's insane. It was an expensive candle too, dude. It was like $130.
Huh?
So it was a really expensive candle. So I'm like, okay, well, I got
It's
to
like
try to save.
handmade
No, I don't know, dude. Anyway,
by like
so
a Native American mystic.
I don't know. It was at it wasn't the candle store that always has the fat black women. It was all liberal white women.
You got to go to the the Asian.
Bath and
candle
Body
store, man.
Works is the one with the fat black women.
What? That's changed.
Oh yeah, no, it's always fat black women in Bath and Body Works.
Really?
Yes.
Back
And
in the
then,
midst
like,
of
it
time
was
when I
Pottery-
was in the
Pottery
U.S.
Barn, that's what it was.
Okay. Oh well, Pottery. Everything at the Pottery Barn is
Anyway.
expensive, right?
And it's all fragile, which I thought. Anyway, I was annoyed. By that. Anyway, so my nephew and I, we were trying to figure out, because like I had to melt down the wax, and try to put it into a different jar, and I was able to do it. It actually turns out it's not difficult at all. But I was like trying to calculate, okay, how many candle jars do I need? And because it was like a weird shape, and so I'm like, oh hey, you know what? Let me pretend I'm in 10th grade again, and let's do some calculus. And I calculated an upper bound and a lower bound just to be safe. So like I pretended, you saw the shape. It was kind of like a flower pot, and I'm just like, okay, pretend it's the cylinder with the narrowest diameter, and pretend the one with the biggest diameter, and those will be my upper and lower bounds. And then I did the fancy calculus calculation of like pretend, to get the precise area, and then I got something that was like 20% bigger than my upper bound, and I'm like, I don't know, dude. I don't care. You know what? I'm just gonna guess. And I bought 3 things, and I only needed 2. So oh well. So
well, you got to charge them $140 for that because you made a candle.
Dude, it was. Anyway, no, dude. And then I went to Pottery Barn to like ask them, hey, do you have like stuff for because I figured like this would maybe be a problem, and they had the candles on clearance, and they were like $30 each, and so that's where I got those. But they were $130 when my wife bought them.
Whoa, dude.
Yeah. So it's just
Goodness.
Anyway, so what was I going to say? So an equivalent statement is that the set of n vectors is linearly independent precisely when the determinant of the n vectors is non-zero. So the determinant measures the volume of the shape spanned by the vectors. So if the span of the vectors kills one or more dimensions, then the volume of the resulting shape will be 0. So visualize in 3 dimensions going to 2. You have 3 vectors that are all coplanar. the 3D volume of the weird 3D mutated parallelogram
Oh,
thing.
kills one or more dimensions. So in 3 dimensions, if we're all in the same plane, we're looking at a 2-dimensional thing
Right,
anyway.
and the volume of that is going to be
killing a
0.
dimension. Right. Okay.
Right.
That makes
So
sense.
then the vectors, but if the volume is not 0, then the vectors must not be coplanar. So you just calculate the determinant, and that tells you whether or not they're linearly independent.
I love this idea that you can have like a 5-dimensional shape, but if one of the dimensions is 0, it's a flat, it's a non-volume, as a 0 volume, but all the other dimensions together would if you got rid of that one.
Yes. However, this is actually a mathematical term. Almost every point, almost every matrix, almost every, you pick 5 random vectors. Okay, you pick 3 random vectors in 3 dimensions. What's the odds that they're all going to be exactly on the same plane? The probability is literally 0. It's like the probability that you throw a dart at a dartboard and it lands in the exact center. It's technically possible, but the probability of it is 0.
Okay, well, actually, when you originally like posed this line of this train of thought, I was like, in my mind, I'm just like, okay, make up vectors in my head, and it's like they're all over the fucking place. Why would any of them ever be like related in this way?
Yep.
Yeah. But then I go plot a shape that I want, and everything is like these.
Yeah.
Every one of the independent shapes that might make up like my polygon snowman or whatever, they're all little triangles. Well, there's the reason I had actually asked, like, is there a way to determine if they're on the same plane, for example, in like a 3D space, is because sometimes that's a really good thing to know when you're trying to plot something or deter like hit detection or anything. Like there's a whole bunch of cases in like game programming where you would care about this. You do, and we usually make slightly fuzzy approximations and zone approximations. We have I mean, we cheat. Like everything in game programming is cheating.
I don't know if the determinant would be good for fuzzy approximation. I don't know. It might be good. It might not be.
We do fuzzy approximations because that's the best we can get because our math is kind of retarded.
Right. Well, and so if I was doing that fuzzy approximation, what I would reach for, knowing, being a world-class expert in game programming, having programmed Pac-Man once, and what I would do would be I would pick a plane and then I would look at, the triangle, and I would look at its coordinate in the axis that's perpendicular to the plane.
Okay.
I would project it to the axis that's perpendicular to the plane, and if that's below, 0.01 or something, then I would say
like the way that this winds up playing out, and the reason it's always fuzzy in the first place is that everything you wind up doing is a little bit fuzzy because you might have like a coordinate system inside of like zone management in the game that's completely abstract space, doesn't even care about like what's rendered, but on the side where you're trying to render the actual game itself, everything is in reals, and that's what your graphics cards like you're trying to play to the silly arithmetic mistakes that we've made over time that have compounded into like having hardware that's really good at doing bad math. And so you lean into that and you say, okay, well, we're going to kind of we're going to make some, in the end, you have to make sure the game just doesn't make like retarded decisions all the time and confuse a player. So that's the same thing with AI too. When you're like programming like the bad guy AI in a game or the good guy AI, you just want to make sure it's not absolutely like retarded.
It's not going to be like my baseball game.
So it doesn't look like, what was it, baseball? MLB The Show or something like that?
Yeah, MLB The Show, the AI. Well, I haven't played the recent games, but the ones from 10 years ago, the AI was just awful.
So you don't want those mistakes. And then when it comes to like LLM stuff also, that's also kind of the index of reasonability is like, is this at least not retarded? And that's actually a hard, in games it's easier because you have a limited scope of interaction with like what we're doing with LLMs today. It's very clear where the dividing lines are all the time because people are trying to people ask LLMs like for relationship advice now, which blows my mind. But I don't know. I guess what would it be, like the sum average of all advice columns?
Yeah, probably. I think about that. Anyway, so regarding the sign, so in general, the sign bit of the determinant encodes whether or not the handedness in the resulting space or the orientation is the same or different from the original basis vectors. So this is called the standard basis, where, you know, zero. Fun fact, every basis is the standard basis according to itself. So, right, you pick these, you know,
Okay.
right, so you pick these two as your basis vectors. As far as these vectors are concerned, I'm 0, 1, or I'm 1, 0, and you're 0, 1.
It's kind of what I was asking before, but
Right. That's what I was trying to get at. So every basis is the standard basis according
okay.
to itself. Right. So the point of linear algebra is being able to kind of smoothly transition between these. The determinant depends on the order of the arguments, and transposing two of them flips the sign. So notice if we have foo x times bar y minus bar x times foo y, if you flip bar and foo, you get bar x times foo y minus foo x times bar y, so minus the previous expression. And the sign bit is 0 if big data sat on your hand and crushed it. So algebraically, with our definitions, the spread is x1 times, it's the determinant squared divided by the product of the quadrances, which is the sine squared. The cross is the dot product squared divided by the product of the quadrances, and that's cosine squared. The Pythagorean identity is actually just an algebraic identity in our terms. So the quadrants of V1 times the quadrants of V2 is equal to the dot product squared plus the twist squared. So spread plus cross is equal to 1. You notice the common denominator here. So you multiply by the common denominator. Spread plus cross multiplied by the quadrances. So determinant squared plus dot product squared, that's equal to determinant squared plus dot product squared plus determinant squared, that's equal to the product of the quadrances. So x1 squared plus y1 squared times x2 squared plus y2 squared is equal to x1 times y1 plus x2 times y2 all squared plus x1 times y2 minus x2 times y1 squared. This is called the Euler something or other identity. Exercise, do that yourself. It's very tedious. It's extremely, extremely, extremely worthwhile to at least once get a pad of paper and expand all of that out and convince yourself, yes, everything cancels out, because you'll get some mechanical intuition about why all of these things cancel out.
Right. Yeah, that's the only way that they actually make sense to me, and that I start
Right.
depending on them.
Yes. Well, it's kind of like jujitsu, dude. You go to jujitsu and like you watch the instructor do something, and you're like, dude, oh yeah, I totally get it. Then you go try to do it, and you're like, what?
Where was
Which
what?
leg? Yeah, what's going on? Right? And that, can I see it again?
Yeah.
Okay,
Oh,
no, I
yeah,
get it.
yeah.
Wait, what? Yeah, no. So like math is, everything's that way. Language is that way. There's a huge difference between doing something and seeing something.
Yeah, yeah.
So-
You watch a Twister and you're like, I can do that. Yeah, sure you
Yeah,
can.
no, yeah. Anyway, not going to write out all of that because I don't want to, and let's be honest, you wouldn't actually read it. And furthermore, the tiny subset of you who would comb through all of that algebra are the same people who are doing the exercise right now instead of reading this paragraph. So let's throw in complex numbers just for fun. So we have Z1 is A plus BI and Z2 is C plus DI. And the complex numbers I squared is equal to -1. So we
You won't
multiply
remember
these.
FOIL, but I only remember that that's an acronym. I don't remember what it means.
First, outside, inside, last. It's just the distributive property.
Ah, okay. Oh,
Yeah.
and you have comments right there, which I didn't even notice.
Yeah, FOIL. Yeah, so you do the FOIL, and weirdly, you get AC minus BD and AD plus BC. So,
But that's okay.
Yeah, so you get the determinant as the x coordinate,
Uh-huh.
and you get the dot product. You get the reversed dot product as the y coordinate when you do complex number multiplication.
ACPD. Okay. Last I equals -1, right? So he's gone. What's I do?
So this identity,
Mm-hmm.
this is just algebraic identity.
Mhm.
It says that the quadrants of the first complex number, they're typically called z, the quadrants of z1 times the quadrants of z2, so this times this, is equal to the quadrants of the product, because this is what the product is,
Mm-hmm.
right? And so this squared plus this squared is equal to a squared plus b squared times c squared plus d squared. So if you take the square root, you take two complex numbers, the length of the product is going to be the product of the lengths. And also the angle in polar coordinates, the like theta value is the sum of the theta values. So you multiply the lengths and you add the angles with complex numbers. That's what happens.
Oh, okay, right.
Yeah, they're really pleasant to deal with. So let's
And
consider.
in this case, this is the only angle that we actually care about going by this system. We haven't actually touched.
Yeah. So let's
We're not
give
even
a
touching
concrete
sine,
example.
cosine, and all that.
Yeah, we're not even touching that right now. So concrete example, you have two lines and you need to find the point where they meet, right? This is like your high school. This is like what everyone did in high school, right? So usually the problem is given to you in some form like, a times x plus b times y is equal to p.
Yeah.
C times x plus d times y is equal to q. Your task is to find the pair of numbers x, y such that the equation is true, right? So doing the problem mechanically is super valuable. There's a reason that this is like what you do for years and years and years in school. The equation, like visually, it's obvious that the equation has a solution if and only if the lines are not parallel. So I'm going to try to connect everything I just said with this. So let's just
your
focus
childhood trauma. I have kids going through that right now.
So let's just focus on what. Well, maybe this will help them. By hey, all this other stuff you don't, this thing you don't understand. Here's how it relates to a bunch of other things you don't understand too.
Well, the older ones maybe, but yeah.
That's the Peter way. All right. Let's just focus on one equation. So we're just going to pick one of them, and we're just going to set p is equal to 0. Okay. So a times x plus b times y is equal to 0, right? So this is a dot product between a, b, and xy, right?
Mm-hmm.
So when the dot product is 0, that means they're perpendicular. So this is asking, what is the set of vectors xy which are perpendicular to the vector AB? So we take AB, which are the coefficients, and when we're solving ax plus by is equal to 0, that is the line, which is what is the set of points that are perpendicular to AB. So we know 0, 0 is a solution. The definition of the origin is perpendicular to every vector. The answer is that it's precisely the line through the origin which is perpendicular to the vector. So this is what it looks like in general. So this is when p is 1, this is when p is 2, this is when p is 3. This is when p is -1, p is -2, -3. Does that make sense? So if
this
we
was the pencil value thing.
Yes, yeah.
I'm trying to remember the terms here.
Yeah.
Is that a general term or is that a Wildberger term?
I think it's a general term. Parallel pencil. but I've only ever heard Wildberger use it.
I've never heard that before.
But anyway, so again, let's set A, B to be E1. So this is 1 times x plus b times y is equal to 0. So when we say p is equal to 1 up here, so a is 1, b is 0, this is just x is equal to 1, x is equal to 2, x is equal to 3.
Mm-hmm.
If we go here, this is going to be x is equal to minus 1, x is equal to minus 2, x is equal to minus 3.
Mm-hmm.
If we go here, same business. We go here, same business. If we go anywhere on the unit circle, you'll see that AB equals the green line. And then if I go outside the unit circle, then I'm here. If I go inside the unit circle, then I go out. By the way,
Why
this
is that?
because Wildberger's version of relativity. But basically, so okay. So the unit circle is the set of points where you take the dot product of that vector with itself and you get 1, right?
Yes.
Okay. So here, inside the unit circle, AB, if I take the dot product of this with like some random vector that's collinear with it, it
Mhm.
shrinks that vector, right? It's like a shrinking effect.
Oh, okay.
Right, so in order to get 1, I have to go way out here. If I'm out
Oh.
here, it's a magnifying effect, and in order to get 1, I have to go way back here. So actually, they're like perfectly dual. So like if I pick this point, and if I go back here, you'll see that like they're actually just dual with each other.
There's something that has an interesting feel to me about that.
Oh,
I don't know
there's
what it's
so much
connecting
here.
to.
There's so much here. There is so much here, dude. There's so much here. Anyway, so this concept, this is called a covector. So the way to think about covectors is that each one corresponds to a family of parallel lines. It's the family of parallel lines to which the vector is perpendicular. So easiest way to visualize it for now, play around with the GeoGebra, draw some pictures. VW is the magnitude of V times the magnitude of W times the cosine of the angle between them. Think of this as measuring the shadow that the point casts, that some like random point casts on AB. So assuming AB is the surface of the Earth, which is flat and it's noon. So like go here, and we just pick it here. Like this casts points over here, and it's like noon, so the sun's shining directly down. These cast long shadows on AB,
Mhm.
right? These points, this point casts like no shadow, or this one casts no shadow. You get the point. If AB and X, so if AB equals 1, 0, then the shadow just measures the X coordinate. If AB and XY agree in their general direction, then the shadow will be positive. If they're exactly at right angles, the shadow will be 0. If they disagree, the shadow will be negative. So far we
right.
understand
Okay. Yeah.
the equation AX plus BY equals P corresponds to the family of parallel lines which are perpendicular to the vector AB. So now we can add another moving part. So we know from being apes that the lines intersect if and only if they're not parallel.
Mhm.
So with the covectors in mind, we can now see that the lines intersect, i.e. the equation has a unique solution, if and only if the covectors are independent. Because that means that the family of lines that they correspond to, if the covectors are dependent, then they correspond to the same family of parallel lines.
Oh, linear independent, linearly
Yes.
dependent. Okay.
Yes. So generally, it's useful to write systems of equations like the above as a matrix product. So ABCD times XY is equal to PQ. Okay. So the rule for matrix multiplication, we use row column indexing. The RCth entry in the result is the dot product of row R of the first argument with column C of the second argument. So I take A1, A2, A3. You imagine taking this and like grabbing it, rotating it, and plopping it down. That's the way I always think about it. And then that gives me the C here. Then I take this one, plop it over here. That gives me C2.
Hang on. I write libraries for stuff like this, and then I never look at it again. So I always have to remember. I wrote a matrix multiplication thing for you a while back too, and like I just don't remember the rule. Okay, we'll call it yes. Dot product of row R with column C. Dot product of row R.
That's how I remember it.
Okay.
So matrix multiplication is not symmetrical. So far we've been thinking about the rows perspective, and that's nice because it's concrete and tangible. And equally, so that's an equally powerful, if not much more powerful perspective is to instead think about the columns. So this is when we think about the problem above this, points and lines problem, instead as a problem that's a little bit harder to visually intuit, which is we look instead at the vectors AC and BD, and we say, what linear combination, what weights do I need to apply to them so that I can get PQ?
What's this formatting? I was going to ask you about the one above it too, but what's this way that you formatted this?
This was me in Vim trying to not have too much noise.
Right, but I mean, there's a reason you did it this way. What's that reason? Like we've got our inner brackety.
Oh, this is just to note that this is a matrix here.
Okay.
This is a matrix. This is a column matrix. This is a 2x2. And then this is...
Oh, I see. All right.
Yeah.
I got you.
No. It's not this
it's not
way.
Two lines.
And then, no. God, no. Sorry. I should have been more clear about that.
Okay. No. That's why I was asking, like, how should I read this? Okay.
Yeah.
So ABCD times XY equals X times AC plus Y times BD, and that gives us PQ. Right. Yeah.
Yeah, it's the exact same thing. So we now think of X and Y as what weights do we apply to AC and BD such that when we do the weighted sum, we get PQ. And this is a lot nicer because our connection to spans and determinants and whatnot's a lot more straightforward. Mm-hmm. So this equation has a unique solution if and only if the vectors AC and BD are independent, right? Because if they point in the same direction, then best case, they're the same line and then there's a billion solutions, or they're different lines and there's no solution. That hasn't, if and only if they're independent, if and only if PQ is in their span, if and only if the parallelogram traced out by AC and BD has a non-zero area, if and only if the determinant is non-zero, if and only if,
yeah,
because that's the signed area of the parallelogram, if and only if no non-trivial linear combination. Non-trivial just means not every single, at least one of the weights is non-zero.
Okay.
No non-trivial linear combination of AC and BD can construct the zero vector.
Okay.
The other useful perspective, so there's the rows perspective, the columns perspective, and the third perspective is the linear transformation perspective. And this is where we think of the matrix as a function that maps the source space into the destination space. And those functions are called linear transformations. It turns out that linear transformations will map a shape that has size S, so like area S, into a shape of size determinant times S in the destination space.
Linear transformations map a shape of size S into the source space.
So very concretely, it's the determinant is you take the unit square and you look at the size because that's literally what that parallelogram thing is it's like, what is the size of the image of the unit parallelogram?
Okay.
Or of the unit square, because, okay,
To a shape of size.
here, let me just, okay, talking about this.
Seems like
Okay.
this should be visualizable.
This is visualizable. Okay. So let's take this matrix A11, A21, A12, A22. Okay.
Mhm.
I want you to imagine that we're multiplying this matrix by the column vector 1, 0. Right. We're multiplying it by E1.
Okay.
In the first,
Okay, right.
we're going to get 1 times A11 plus 0 times A12. That's going to be A11. In the second coordinate, we're going to get 1 times A21 plus 0 times A22. So multiplying by E1 just gives us the first column.
Mm-hmm.
Multiplying by E2 just gives us the second column.
Okay.
Right? So I take the identity matrix, which is 1, 0, 0, 1, and I say, and I pretend that that represents the unit square, right? 1, 0 and 0, 1, because those are the vectors that correspond to the unit square. Right? Where's my determinant signed area thing? Where is it?
Is it a different tab?
Oh, yes, it is a different tab. Thank you. So I have one. Okay, this is the unit square.
Mm-hmm.
Okay, and I'm just going to map it to like here. Right? So B, this vector, is where does 0, 1 go? A, the first column, is where does 1, 0 go? So therefore, this parallelogram is where does the unit square go? This parallelogram is the image of the unit square, assuming these two are the column vectors in the matrix.
Okay. But this, you're doing like the 0, 1 coordinate and the 1, 0 coordinate, right? The matrix multiplication only works if you have that. Like, this is all one group together. Like, you can't really separate these ideas and get anything.
I don't understand your question.
You're saying like so the elements you're putting, so you have a matrix that you want to multiply, but you're multiplying against this other thing. It's not like this is all one big idea together.
Sure.
That you're gonna, it's not just, oh, this matrix does multiplicate. Like there's a whole system around this with an operation together with it, and this idea that you're gonna have these perspective coordinates that you're gonna use to try to get this image out of it.
Well, I think what is confusing you is that I am sort of making the concept more complicated than it actually is mathematically, because I'm trying to relate it to visual intuition. And that necessitates thinking about the matrix, okay, so the matrix that has, where are we? Okay, so the matrix that has 1s on the diagonal and 0 everywhere else, and that's a square matrix, that matrix is the identity matrix. So it behaves as the identity function. You multiply it by any matrix and it does nothing. So when I'm taking this matrix and I'm multiplying it by 1, 0, that's just giving me the first column.
You're getting the same thing back.
Right. So I take this matrix.
That's the identity matrix for multiplication?
For multiplication, correct. Yes, for matrix multiplication. And what I'm saying is, let's think of the identity matrix as describing the two vectors. Where are we? That correspond to the unit square. So we're going to pretend that the identity matrix So we're thinking of the matrix as multiple things. We're thinking of it as both a transformation and as a list of coordinates. This is kind of what's tricky about, you know how mathematicians, we don't really care for types, and we'll like pretend that vectors are numbers, and we're like, yeah, let's multiply, a point by, I don't know, a squirrel. And that makes
Yeah.
perfect sense in math, and it drives programmers nuts.
Yeah, because it's like stop
Right.
implicitly making up operations.
Right. But in mathematics, we care about the structure of things, not what things are.
Okay.
So we're thinking of the identity matrix. So the matrix 1, 0, 0, 1. We're thinking of the first column 1, 0 as saying,
I like to add at the bottom. It says overwhelmed.
yeah.
That's funny.
Yeah. So 1, 0. Okay. And when I multiply that by this matrix, I'm saying, where does the vector 1, 0 go? Right. I'm thinking of this as a function that takes points in the plane to points in the plane.
Mhm.
Okay. If I give it 2 points, I can say it takes 2 points to 2 points, right? Because adding a column, adding a column to my argument. So something that's kind of visually obvious to me that I probably should explain, like make really, really explicit. Okay. So if I just pretend that these other 2 columns don't exist,
Mhm.
right? That 2 through 9, this block doesn't exist, then 2 through 9 over here wouldn't exist, right? I would get, this is a 3 by 3 matrix times a 3 by 1 matrix.
Mhm.
So I would get a 3 by 1 matrix out. If I add this column here, it's basically like doing another computation. This is how GPUs work. This is why GPUs are like super trivially parallel and why they're good at matrix multiplication. I add another column here, and that's just like adding a parallel computation. Right. So I'm saying, right, this first column here, this is where 0, 1 goes, or where 1, 0 goes, is here.
Mhm. Right.
And this is where 0, 1 goes.
Mhm.
And so this parallelogram is where that unit square, everything that's in that unit square is going to go somewhere in this parallelogram.
Mhm.
And so the determinant is the ratio of this area to the unit squares area. And since every area in the source space is measured relative to the unit square, you can think of like tiling any area or triangulating the area of something. If it's this sort of uniform distortion. So a linear transformation is the generalization of multiplying by a constant. That's what this is. This is the higher dimensional generalization of multiplying a number by a constant.
Okay.
Yeah, that's those are the only one-dimensional linear transformations, are where you take a number and you multiply it by a constant.
Okay.
This is
And
the
that,
higher dimensional generalization of that. Yeah, go ahead.
okay. No. It's the one-dimensional version is where it feels easy because you feel like you're dealing with sort of a number line, but then when you add components, you're adding dimensions, and so you get this visualization. Okay. Yeah.
So, dude, for the fact that this is your first time encountering this, you're doing really well. So most mathematicians take years and years and years to wrap their heads around this. I would say the majority.
Well, I still want to work it out by hand though, because it'll make more sense to me then.
Yeah, absolutely. So it maps a shape of size S in the source space to a shape of size determinant times S in the destination space.
Okay.
The sign.
That makes more sense now than it did the first time you read that sentence.
Yeah.
Okay.
The sign captures whether or not that orientation is inverted. So basically,
yeah, right.
Right hand, does it go from right-handed to left-handed?
Right.
Okay. So back to our
which
campaign.
We don't normally care about though in area, except other than like canceling shit out to find the area when we were doing other computations.
Yes. Yeah. It's like extremely crucial and fundamental though. Anyway, so we're almost done. So we're gonna go back to our campaign of exposing the shocking truth. So we're gonna back up a minute. We're gonna look up our original data. So
I love
far,
that the clickbait title of this video is so ridiculous.
Yeah. So our original data. So we've been thinking about this data from the rows perspective. So we're thinking about this table as like a list of records, right?
Yes.
Yes. So with what we just learned in mind, we're going to do like a lists on zip type situation. So we're going to do the heights, which is, pull out the height field. We're going to pull out the weight field, and we're going to call that weights. And we're going to take that matrix. So the heights here, the weights here, those are the two columns, and we're going to multiply it by its transpose. And again, matrix multiplication is not symmetrical, so the order really matters. So generally the rule is you have an A by C matrix and a C by B matrix. The middle two have to match because the dot products have to be computable. Okay. And the middle cancels out, and the dimension is A times B, so it's the outer dimensions. That's why I was saying, oh yeah, you can just trivially make it parallel by adding another column. Duh. Right? And that's a super not obvious intuition. You just have to have done a billion matrix multiplications by hand to get it. So, right. So viewing our matrix as a matrix data, there's two possibilities. So let's call the number of entries n, so that data is an n by 2 matrix. If we compute data times the transpose of data, that's going to be n by n, which might have some information, but it's way too large for us to look at it and read it and ascertain anything useful because we are not big data. If we instead do the transpose of data times data, that's a 2 by 2 matrix, which when you normalize by 1 divided by n, that's called the variance covariance matrix. So 1 divided by n, so you just normalize by the number of samples. Really, you should weight it, in general, you should weight it by the probability distribution, but we're assuming that every point is equally likely in our probability space. Okay, so we're pretending. So,
which do we care in this type of?
In this specific situation, no. But again, I'm simplifying. Right? I'm trying to minimize the amount of detail we have to account for. Okay. But we do have to divide by n, because we have to take an average. That's why.
Aha. So, okay. Right.
So if you've heard the terms, so this thing that comes out in the right, on the diagonals. So this is going to be each column dot product with itself. So this is going to be the heights dot producted with the heights. And again, very crucial, very extremely crucial is that we changed our problem so that the median or the mean was at the origin.
Right. So we've already got one transition before.
Yes. Because otherwise this is a giant mess. Because you have a bunch of minus signs and you have to distribute a bunch of matrix multiplication. It's a nightmare. Okay. And then you have to add and subtract. No, fuck that. Okay, so the diagonal entries are called the variances, which are the covariance of a variable with itself. So if you've heard the term standard deviation, the variance is its square.
The variance is its okay.
Is the square of the standard deviation. In our terminology, the variance, it's half because you double count, but it is Notionally, it's half the mean pairwise quadrants between data points. It's half because you're double counting when you take the mean pairwise quadrants, because the quadrants of A between 2 points
Mhm.
is the same as if you do it in reverse. So the variance is the mean pairwise quadrants between our data points. And the algebra for that is fairly straightforward, but I didn't feel like doing it.
Exercise show algebra.
If you've heard people throw around the term correlation, the square of the correlation is the covariance. So in our terminology, the covariance is the mean pairwise cross, half the mean pairwise cross between the 2 points. Between 2
Half
points.
the mean. Okay, right. Okay.
Right. So it's basically how close are these 2 points to each other directionally on average. And so
right. Yeah, because
really
we've already. Yeah.
If that's really high, they're very strongly correlated variables. And if it's low, if they have zero correlation, then they're independent. Then they're variables that have nothing to do with each other.
Okay.
Right. So that's cross. That's cosine. That's just, directional similarity. We're almost ready to expose big data and talk about those best fit lines, but we've been here for 2 hours, and we do need to talk about matrix factorization, which is a lot, and we need to learn about fake German words like eigenvalues. So I guess that will have to wait until next time, which is why I put heartbreaking in the title.
Well, and it's part 1.
Yeah, it's part 1. So anyway, I don't know if that's why big data is upset, because he wanted to know about the rest of this, or if he's upset that I'm exposing him.
He's afraid of having to move to Houston to go visit Dr. Now because of his Ruffles problem.
Well, how is he going, like, physically? Can he even fit through his doorway?
They find ways around that, apparently. Like,
dude,
I've seen clips of that show. Dude, I've seen clips of this show. They have the whole fire department show. It's funny too, because firefighters, all they do is work out and run upstairs, and they wind up looking really small to the task.
Yes.
Like the whole fire department.
Yeah, and then you put them next to an average person. It's like the buffest dude you've ever met.
Yeah, they're like, we're manly men. They're like, oh, we need more. It's like
moving a 600-pound futon.
Yeah. So they get safety blankets to because they can't. It's really sad. And then these people try to drive. There's multiple of them that they fall into the back of a van or an SUV and just sort of spill out to fill the space like a liquid with some bones floating in it. They're like Wall-E people. And have you seen Wall-E, the cartoon movie?
No.
The story's fine. It's a good movie, but there's aspects to it, like the setting or the setup for it is really funny in kind of an Idiocracy way. It's like Idiocracy for kids is the world that they're in. And the only two sane people in it are these robots. Because the people are they're like giant adult babies.
Little Data.
Yeah. Yeah, but similar kind of proportions. It's like the problem that you see in some lots of countries that have an upper middle class sense of things for the first time ever. Like a lot of Europe is that way, a lot of Asia is that way, and obesity is going down in America for the first time. And yet, I guess it has been for a little bit now, but so Americans went on this massive health kick, and everybody's either a giant whale person or they're mega buff and into working out. There's not much in the middle, it seems. But in all the places that used to make fun of the United States for being fat, you see these egg people.
Yeah.
And they have this weird, in Asia in particular, they have this way of getting fat that's very smooth, and they look like eggs wearing tights. And then they have little egg children that are glued to an iPad or something. And if you pull it away, they flip out. They just waddle around. Dude, and they eat snacks.
I it seems to be dying down. I don't see a lot of kids anymore, but
I really hope that goes away. Like
but dude, I totally get it though, dude. Like you go on a plane and like your kid's freaking out and being an asshole, you just give them an iPad and it just like solves the problem and the kid just shuts up and is perfectly well behaved. It's just an angel and he just sits there. And
we take like playing cards and stuff. We'll take like a bag of like little toys like and playing cards and stuff and talk to them. And occasionally you got to give the dad look or the voice. It's like, hey, and they know that exact voice. You're like, oh, cool. I'm cool, man. But you know, but the iPad, I just like the destructive power of like social media. People are like, social influencers are destroying my kids. It's like, why did you give your kid social media? Like, don't do that.
Yeah, I mean, I don't know. I mean, I don't know how practical it is to try to like really keep your kids off of. I mean, I remember being a kid with a computer and like the thought that my parents were actually going to have any sort of say over what I was doing on that computer was laughable.
Right.
So like, I mean, it's kind of, I mean, I guess kids these days don't have as much computer knowledge, but it's still like, okay.
Well, that's weird too. Like when I was a kid when I started at phone freaking, like you learn real quickly that you gain a lot of intuitions about not just how like electric current works, but how the phone system worked because you were playing with it. But when we got modems and we're like, hey, we don't have to build stuff anymore, we can program it. That anybody that I like, most people that I met online, I say online, this was like dial-up BBS days, but the people that I was meeting, almost everybody thought that I was like in my 30s, and I thought they were all kids, not realizing that I was an extreme minority of kids who had managed to even figure out what a BBS was and get in and do that. And so it was a very mixed sort of world, but everybody there was unified by the fact that they had all managed to even show up.
Yeah, it was pre-Eternal September.
Eternal
September. So it was this thing back when the universities would were like how you would get access to the internet was you were at a university, and every September the new freshmen would come in and they didn't like know how to not be assholes on the internet, and so they would come on the internet and it would just be annoying every September, and then AOL came along, and then it was Eternal September.
Okay, I get it. So remember back when Stack Overflow was a thing? We once like the subcontinent got online, we had that problem every time like the Indian academic year would start. It was like, do my homework for me questions, which is like millions of them, like that fast. And that's when moderation had to become like a really big, heavily charged thing. That's when capture happened, and that's when Stack Overflow started.
Have you read those articles about like fucking Boko Haram using ChatGPT? Dude, okay, so just keep in mind the Gungans that you were deployed with in Uganda. Those people probably have smartphones now, and they have ChatGPT.
Oh, dude, they got one shot. Like everybody that used to work for me is like poor now because of online gambling because they got smartphones.
Yeah, but
like it one shotted them that fast, and now they're having relationships with relationships with chatbots. It's really crazy. Boko Haram, I'm like, wow. What's going on? What's is there like a specific dynamic?
Well, they basically will be like asking ChatGPT. They're like, "Wow, our enemy is in this castle. How do we get rid of them?" And it's like, get a ladder and climb over the walls. And they're like, "Oh my god, I didn't think of that."
Well, they don't often think of much.
They'd
be the only fighters in Africa that aren't like addicted to Wadajin and other stuff because like it's haram.
Yeah, but like it just, dude, okay. Here's the thing. Whatever I think about Islam, when I watch documentaries about like from like where they're like have camera crews with the soldiers in Afghanistan where they're like trying to work with the native soldiers. They're like, we just can't get them to stop using opium. And we just
Yeah.
want them to like stop smoking weed all the time and stop getting fucking stoned out of their
Yeah.
mind so that they can
Well,
like fight.
there's
And the Taliban like actually has their shit wired tight. And
well,
that's
that
why
was the big mismatch. Like the guys that you would see in the especially the normal like Afghanistan, there were some like sharp dudes in special operations that you know my initial view was very skewed by only dealing with them. But the average like Afghani soldier, they were like literally rejects from their village. That's why they were there. Like, so you already had a bad subset within like all you're just baseline is Crazyland, and then you've got the rejects from Crazyland that show up in the army, and most of them have accepted that they're just going to die anyway. So all they want to do is get high. Then you go like do a meet with the Taliban guys, and yeah, comparatively they were pretty squared away. They weren't drunk or high all the time, and they knew they could identify what their own side was and why. And like,
yeah,
just
and they're
if you
like,
begin there,
wow,
you
it's 6 o'clock. I should get up.
yeah, right.
They can make that sort of connection. They can read the clock.
Yeah,
Like
they weren't
like
completely, and they had a couple of people that were like legit sharp too, and those people were worth talking to. And you got this sense where if I read like back, like you talked to the Vietnam vets that were teaching the engineer course when I was going through SFQC, and like they would tell you that sometimes you'd get this sense that they're kind of on the wrong side because they're on the side of all the weasels and losers. And when you're on the side of all the weasels and losers, you're on the wrong side basically because they're not going to be the drivers of national determination for this area. So you're already kind of doing something wrong. And that's like that stuff just comes right back to mind after you meet people that are locked, like, I mean, it's not politic to say, but the Haqqani Network dudes, they understood. They totally knew the score, knew what was going. They were just waiting stuff out, because they knew what was going on. But
I read it was back when I was like super liberal, but I read Ronan Farrow's book about Afghanistan. He worked for the State Department. I think he worked directly under Hillary Clinton, and he was like a State Department person. Ronan
I haven't read
it. Yeah, it's called. Oh, I can't remember. I read the book. Ronan Farrow's an excellent writer. And what was I going to say? Basically, the sort of situation that he described was like kind of from the State Department's perspective. They go there and they're like, okay, well, the Taliban's obviously going to win, and we are just going to sit here. The only thing that's stopping them from taking over is the fact that we're here, and literally the instant we leave, they're going to win. And then guess what happened? The instant we left is the Taliban took over.
Yeah.
And that was obvious to him in 2008. He was just like, okay, this was just, everybody just understood that this was the situation. And they're like, okay, well, we can either like do we don't negotiate with terrorists thing, or we can negotiate with the terrorists because the terrorists are the only people who aren't high all the time.
Yeah.
And
well, there was a lot of misconceptions with like the way that nation building creep kind of gets in is you wind up, they keep redefining what victory is.
It's just fucking ridiculous, dude. It's like, yeah, okay, these people like, they're like goat farmers from the 6th century. Okay, they don't know about democracy. They don't know what George Floyd is. Okay, they don't care about trans rights.
Well, that's when things are like fully lost in your own sides, like actually that shoot up one now.
The only people who like are like who are not in the first world who like enthusiastically care about trans rights. Okay, aside from like the whole ladyboy thing in Asia, but that's like a different thing.
That's a different thing, yeah.
That's a different thing. Like what it is that you'll go to like, and I'm sure Mike will chime in. Mike's from an undisclosed country in the in Eastern Europe. But like, you go to Eastern Europe, the former Soviet Empire, and like, people basically fucking hate Russia. They just like unconditionally fucking hate Russia. They hate everything about Russia, and they love the West because it's not Russia.
Yeah.
And so, like, you'll see people adopt every Western symbol without understanding anything about what they mean. So they'll have like a cowboy hat and an American flag, and then they'll also have trans rights, right?
Yeah.
And cowboy boots and like the big, rainbow flag patch, and
Yeah, they'll just adopt. They're just mimicking what they see, but they don't
Right.
know the meaning behind it.
right, because they know that Russia doesn't like those things.
Yeah, there's I don't know, big parts of the world. They have a hate for Russia. I don't know, seems weird to me.
Well,
I-
I mean, I get it. I mean, I wouldn't want to be part of the Russian Empire either.
Well, it
sucks.
winds up being easy to kind of force them into their own self-destruction, though, by saying, okay, Russia's here, and then whatever, like, you're here, Russia's over here, so whatever's not that direction, going the opposite direction, you wind up being able to redefine. You can point them in a direction to react to by redefining to them what their kind of adopted symbols are, so that they go to the opposite direction, but you've picked what that opposite direction is because you're not actually in a linear space. You have much more freedom of movement. And so whatever feels like it is the opposite of Russia, even though there's no such thing as the opposite of a country, right? There's more
Yeah,
options
exactly.
culturally there's
Yeah.
more options than to be Russian or not Russian. There's
It's the
all
opposite.
kinds of freedom freedom of movement all over the place, in terms of like identity. But you set up this idea that this is Russia, and so the opposite of Russia is this. And so we're going to do this super hard. And if you make that a toxic, self-destructive thing, they will jump right into that every time. And that's what's happening.
Yeah, it's weird. I don't know. I mean, both of my grandparents spent time inside, but they were sent to Siberia, and, But I can see things from the Russians' perspective too.
Mhm.
So what people don't understand is Russians. They want to belong. They want to be part of Europe, and that will never happen. And they don't see it that way. That's the sad part.
Mhm.
Because
Yeah,
the Western world has to chip in, hate Russia, and that's all
Well,
there is to it.
but like, ordinary people in the West don't give a shit about like we know Russia bad.exe.
Yeah, exactly.
Well, but
But
you have to have the political, from the
But there's-
political science perspective, the way that they think is that because they can't conceive of a bigger problem to kind of direct the country at, like something that's productive, like a space race or something, they think we have to have an external enemy because if we don't, then we'll lose control domestically. Similarly, if we want to control everybody domestically even harder, we need to break them up. So like we have to have racism or classism or whatever
yeah.
to divide people up. So the West rejects Russia categorically because that's an enemy that's similar enough that you can view them like it's a peer competitor, and there's not that many of those.
But it's also fake, and people see through that. That's the
Yeah.
problem. Back in the Cold War, it was not fake. So yes, it was it was uniting people in the West.
I
Mhm.
remember being in Salt Lake City and seeing these like people blocking the highway to protest about Palestine, and I'm like, nobody gives a fuck about Palestine.
Not really.
Nobody, no, but none of these people, Kate, it was just a bunch of women who, you know what, I'm not going to say that on the stream, but you know where I was going with that thought. And and it was a bunch of college-aged women who had nothing better to do. And like, I was just like, okay, why are we pretending that anyone gives a shit about? Nobody gives a shit about Palestine.
Because the establishment's flailing around right now because they're trapped in this nostalgia for the Cold War. That was a great, great period for the establishment.
Well, yeah, because it justified pretty much unlimited expansion of state power. And
like, you know how you can have like, have you ever, when you have really, really thick ropes on a ship and they're in massive tension and you can basically treat it like a piece of wood, you can like drive nails into it and shit. It's basically a piece of wood. And you start relying on that because you've built up your little hooch on deck around that thing being here. and then imagine it just goes slack one day. The anchor of everything that you built up for your convenience is gone now, and you can't fathom coming up with something else. That's what the establishment is. This is a very, very fuzzy way of saying it, but that kind of thing is going on.
Yeah, it's they literally lost their understanding. That's the way to think about it. And sir,
you just said sir. Are you talking to a cat?
Why would you think that?
Because you have like 57 of them or something?
No, I have 4, Craig. Haven't you read my lease?
4? Oh, dude. No. Yeah. That's like...
Wait, no, maybe I have 2. I don't remember.
You and Cecil, man. She has like tons of animals. That's like what my daughter, that's like my daughter's like dream is if she could have like 1 million pets.
Well, I have to say it's there's challenges of having 2 cats for sure. But I definitely think well, Mike also has 2 dogs. And I would say the positives greatly outweigh the negatives. They're really wonderful.
Is that code for Mike has 27 dogs?
I don't think he has 27, but he has. It's comparable to my situation, and they're all little. I'll send you a picture.
Okay.
Mike has 2 dogs though.
I wound up with 3 cats though, which was not intentional. We have the one-eyed.
Yeah.
We have the pirate cat.
I've got an unlimited supply.
We're good.
Anyway, anyway, they're wonderful, but it can be challenging sometimes.
Well, thanks for the for part 1 of this, and I guess we'll continue with part 2.
I gotta think of more lore having to do with big data.
Oh, to come, yeah, we gotta.
Maybe gotta have like big data going, like get on the forklift and go to the grocery store.
We need to have him shopping like with the bacon aisle. Or like cereal, dude. Like this, people on that show buy like pancake mix, cereal, and bacon, like primarily. It seems.
And dude, they go to the fucking grocery store and they're in the fucking wheelchairs, and they like go and they.
No, they give them the rascal powered.
Yeah.
Multi creature mobility device.
Yeah, the rascals, and they're like riding around, and they see like an end cap, and it's full of Doritos, and they're like, "Oh, Doritos, we obviously need those," and they like grab the entire box and put it in there.
Oh, it's like the whole row,
like end cap. They just put the whole end cap in their cart, and they're like, "Yeah, we'll eat that in like 2 or 3 days. It's just going to be gone."
I always wondered how they afforded like that much food, because like I have a big family and food's not cheap, and so I'm like, how do they afford this? And then sometimes there's a mention of like they have like a disability thing, and it's like subsidized. It's a subsidized pathology.
Yeah,
which is wild.
I don't know exactly. I've never been on food stamps, and I do know people who are on food stamps. I suppose I could ask them. I don't actually know how it works. Here, you basically just get like a debit card, and my understanding of it is that like you go to the grocery store and like every item says it has like next to it whether or not you can use food stamps to buy it. And
here, I've never seen anything. Well, but I mean, it's a whole different system over here. But
I don't know. I mean, it's got to be rate limited, because like you can't it's not just an infinite money glitch. But also, like you go to every store, especially you go to the poorer areas, and it's like selling food stamps or transferring food stamps to other people is a felony. I'm like,
right.
Why
and
is
there's
that
a guy scalping there's a guy scalping sausages out front
on the store, like selling food stamps is a felony, and I'm like, what are you? I'm
like what's the story behind this having to be a sign?
Yeah, and no, dude, I still remember driving in Connecticut, and being on I-95 and seeing this sign saying it's illegal to drive on the shoulder. And I'm like, I've never seen that sign anywhere before. Why do you need, obviously it's illegal to drive on the shoulder. Like the point is that you're not supposed to drive there. That's the whole point. And then I'm
Right.
like, I don't get it. And then immediately like 5 cars come zooming past me on the right shoulder. Like, oh, okay.
Oh man. There, well,
And this is in bumper to bumper traffic, right? Like,
right, yeah, there's no need to be over
jam,
there.
there's people like driving like 65 on the right shoulder next to traffic that's going 0.
I I don't know. That's, it's always sort of quaintly pleasing to go drive in like the Philippines or Malaysia or something where there's just traffic suggestions.
Yeah.
And people just kind of go wherever. Dude, like people try to save gas by turning their lights off in the pitch black in like at night. People
that doesn't save gas at all.
Dude, they like also they have tinted windows, by the way.
Oh yeah, so, and it'll be their windshield that's tinted, right?
Yeah, the front windshield's tinted, and they turn their lights off when they drive at night. And as they sort of see like a glimmer coming, they turn them on real quick, and the other one does too. They're like, "Oh, okay," and then they turn them off again. It's like, okay, it's pretty neat.
Dude, I remember renting a car and driving, and then realizing, oh, it's night, because like I was driving on the freeway and like everything was well lit, and then I got kind of outside the city, and then I'm like, oh shit, my lights aren't on, and I have no fucking clue how to turn the lights on, and there's no light here.
Oh so, man, every time I go someplace like Korea where they drive on the other side, they drive on the right side of the road, right? So where I live, we drive on the left. So when I go to a place like Korea and I rent a car, everything feels normal, and then I have to sit in the wrong side, and I'm like, okay, where's the thing? And so every time it'll take a whole day before this gets normal. I turn the windshield wipers on and smear like sand all over the place, maybe 30 times trying to turn the turn signal on the first day. It's so annoying. But like because the things are on the opposite, like where I live, like the turn signal's always on my right hand.
Oh, right.
And
okay.
Over there, it's like that's the washer and the windshield wiper stuff. So the accessory shit in the car just like goes off all the time every time I try to take a turn. And I'm like, "Ugh!"
No, dude, you're in. Well, I don't know about in actual Korea, but you just embrace the Asian. In America, if I'm inferring based on America, you just embrace the Asian driver mindset and just don't use your turn signals.
Well, yeah, it's that's like frustrating too. And like in my town, everybody's quite polite about all these things, and everybody looks like you look at the other driver because there's not a lot of signage here and stuff, and everybody knows everybody. And then we have this big influx of tourists, and some of them come from places where the accelerator is not on a spectrum. It's just down or up. And also, we've got these signs on the back of all the tourist cars. Like when you rent a car, if you're like a foreigner, there's a sticker that we put on the back of the cars that says, "Be careful, there's a foreigner driving," in Japanese, and then below it in English it says, "I love Okinawa."
You gotta send me that.
I'll take a picture. It's really funny. So there's like, you learn how to spot these, but they don't use turn signals. Like you don't know if it's okay to go or not when someone's coming, if you don't know who they are. And it's really frustrating, but there's a lot of crap. Like, I mean, Summer got like T-boned hard by a tourist that we felt really bad for. Cause they did hit her hard at this intersection. They just decided to take a right turn, across traffic while there was incoming, and they just nailed her, which seems really stupid. I guess they were probably distracted or something,
but also just being Americans thinking, oh, I can just make a right turn. That's just what was going on in their head.
I think they were from like Hong Kong or Taiwan or something, but yeah, they were foreign. And, but they were on the reason we felt bad was like, it was a girl driver. She was a paper driver. So she had her license since high school, but she'd never used it. She came here and rented a car, went through a whole week on a vacation with 3 of her friends, did okay, made it through. This is the last day they were going to go to the airport that evening. And they got in this big car crash. nobody on my side got hurt. But that was like a narrow thing. But like completely blew up their rental car. So they get to not make their flight because there's all this police report stuff and the insurance people come out to assess and all this shit. They're just like caught in this thing now.
Yeah.
And that's what their memory of going on vacation was
Sucks.
getting in a big car crash. And then they felt like, I thought this girl was going to like do herself in because she came over to check on Summer, and I had a baby in the car too. I wasn't there when it happened, but we had a baby in the car too. And she saw that and she was like, just completely, it's like, oh my God, I hit a family van with a kid inside. And, so that was their last memory of like being, happy summer. It's like terrible. What a way to end your vacation.
I don't know. I don't feel like that would ruin my vacation, but
if you hit like a family van on your last day,
I mean, I'd feel bad about it, but it wouldn't like ruin. I don't know. I haven't never gotten into a serious car accident though.
Like she went through that whole thing where she was like, what if that kid hadn't been buckled in? What if there wasn't a child's seat?
Yeah.
Oh my God. Like all those like eventualities. Like nobody actually got hurt. It did totally fuck my man up. But which my insurance company was really good about, and the rental car agency was good about. We didn't actually have a big issue out of it, but that was all lucky.
When you were telling me that, I was like, well, was your family hurt? And then when you said they were fine, I was like, okay, probably your car got fucked up, but also knowing Japan, probably your insurance was just not.
No, they were really, really good about it. And it was a big inconvenience, but like it was mitigated as well as it could have been. And all that safety shit that Honda talks about, it works apparently. So all that did what it's supposed to, and everybody's okay. But the people that hit them it was a bunch of girls, and they were like sort of freaking out, realizing like, oh, that could have been for really real, like that was that close to being something really bad. And that really kind of messed them up. So that was their, drive safe, people. Cars are scary. They're just these like 1 ton blobs flying down the road, and the only thing protecting you is the paint line.
Dude, I've gotten, as you know, I've gotten addicted to watching police videos on YouTube, and a good portion of them are drunk drivers and car crashes, and it's just, oof, car crashes. I mean, they're just, especially on the freeway, dude. It's bad.
Well, dude, like every 10K faster you go, there's just so much more energy in that thing.
Well, and then, and dude, like, the other day I was driving, in my undisclosed location, driving out kind of in the middle of, in these very windy roads with a lot of wildlife, with, the road quality was good. It was daylight. But, I had driven on the road, 6 or 7 times by this point, and I'm like, yeah, I know this, I know the road, and I'm like, and the speed limit's maybe like 50, and I'm driving like 80 because I know there's no cops there. And I'm like, yeah, that's just like, if there were no obstructions in the road, it's totally safe to drive 80. But like, deer can just appear out of nowhere, and boom.
Mm-hmm. Oh yeah.
Deer,
my aunt hit one
passenger car going 80. Bye.
Yeah, well, my aunt, this is in Louisiana, a deer jumped across the road and like got its head, broke through the passenger window with its head, and it snapped its neck on the brace behind it. Oh. And the lady behind her stopped in front of her to come out and says, "Is you okay?" She's like, "Yeah." She's like, "Can I have the deer?" So we got the feeling that like if my aunt had been knocked out from that crash, she wouldn't have asked anything. She was only interested in getting the deer. So, the good Samaritan sometimes. But yeah, that was.
There's deer in Louisiana.
Dude, there's tons.
I don't know why I'm surprised about that, but that does surprise
There's tons.
me.
There's so many that it's like they're like a pest.
Don't you? But isn't that what the alligators are for? Take
That's
care
in
of
like
deer?
that's in the southern, like once you get down to the south part, like around Honeycomb.
Okay.
That's Honeycomb Swamp has alligators all over the place. Like they ate my cousin's dog. But so an albino alligator ate my cousin's dog, and we're like, whoa, but it's an albino. We can't kill it. We're supposed to call the zoo, but it ate the dog. So moral dilemmas abound in those situations. But yeah, the north part of the country is all that's all deer. Like that's what people do all winter is like deer hunt. Well, I guess nowadays they've got this. That's when I was a kid. Now they've got this. There's like a wasting disease or whatever. They're like
Oh,
Jacobson's kind
yeah.
of disease thing. There's a prion problem, and it doesn't look like there's any way to really fix it until we figure something. Like it's a slow moving disaster. If enough money gets put into the problem, it will probably get solved on some technical level. But that looks like a slow moving extinction. I don't know that biology is going to have time to kind of mount a natural defense against that. It's like that creepy.
Mhm.
So also we don't know what happens when people eat those. Like they're not quite the same
I'm
protein.
sure. I'm sure there's tons of people who are eating those.
They are. Like there's been it's a really big non-trivial percentage, but this was like the mad cow thing was like that where nobody knew what the effect of it was going to be, and a few people were like, well, we should probably be careful about this because the biology is kind of similar. We're both mammals. We have a lot of the same whatever. And then it took like a decade to manifest in a lot of people. And if it takes decades to manifest in people that have consumed this, if we have the same conference pattern from human to human that the deer do, then that could be really bad. And it could be this when it comes to deer, you could have things in the food supply too, because those molecules get like those
Yeah,
prions.
they get into the soil.
And then they wind up in
and then,
the plants that
the
grow from that.
livestock eat them.
Right.
And yeah.
So
yeah.
Like of problems that could be really like that's where like all the money that's like wrapped up in like the climate scam, there is a real problem that needs to be focused on. And
I think it's weird that dude, I gotta go to bed, but I think it's just bizarre how a lot of these like leftist pet causes from 20 years ago, they've just stopped talking about them. Like the climate thing, they just don't talk about the climate thing anymore. They've just given up.
Well, it got to the point where if you wanted to do actual climate research, you couldn't if it was on Earth. But if you want to do planetary science and study climate on like Venus or something, it's totally fine. But if you try to apply discoveries from there to here, like the surface pressure thing, like atmospheric pressure correlations, that's like, no, there can only be, because it's a politicized thing that like carbon has to be the one knob ever for everything, which is ridiculous.
The solution.
Yeah, this has to be the solution because this is what we've optimized our political messaging for. Therefore, no more looking at anything. So once you reach that point, it's like, well, whatever funding and all the other shit's going into this effort, we have legit problems that we can like identify right now that are really terrible, slow moving disasters that are absolutely real, like that wasting disease issue, like prion disease. That's a serious issue, and nobody. So like to destroy a prion, you have to like bake it at like autoclave temperatures, like 900 degrees or higher for like a while. That's how durable they are. And there is no timeline by which we know that they dissolve in the soil, and they get picked up by the next, plant life. They wind up in foliage. If you eat vegetables that have that in it because the deer have been pooping on the farm, we don't know what happens to you because this takes so long to manifest. So like, that seems like a big deal. Not to mention the Creutzfeldt-Jacobson's disease stuff that we saw coming from some medicines recently, if you know what I mean. That's a spooky one too. So there's a bunch of weird stuff going on that we could look into, but nobody, I mean, I say nobody, that's not true. They're not public efforts that you can engage in, even though money's too cheap right now for a large, like the economy is still split. You've got this like money's way too cheap for this class of people problem, and then money's way too dear for everybody else. You almost categorically can't get big funding for a good project right now, which is kind of weird. So, but hey, AI bubble, let's go. So,
I think I am well, I shouldn't say optimistic. Optimistic isn't the right word, but I see a lot of signs that it seems like the AI bubble is closer to popping than we think.
I think
yes,
SpaceX is gonna crack it.
What's that?
What do you think?
Cracks in SpaceX is gonna do a cascade of AI failures on the Wall Street.
I don't know. Like, there's a problem that all the fake money that was made up over the last several years that is wrapped up in these mega bubbles has to be kept out of the consumer economy, or else you would get massive price changes that would be absolutely destructive. On the other hand, once these bubbles crash, because most of it's institutional money, you're going to have this huge in the institutional side. You're going to have this huge deflationary thing where like values just get wiped out overnight because everyone's trying to sort of pay back.
Well, the values
on the consumer economy, that's going to be like big job losses, tons of people getting laid off. All these construction projects are going to be frozen. So like the working class is going to get totally screwed. And so you're going to have this massive institutional deflation at the same time that you're going to get massive stimulus spending on the consumer economy. And that's where I'm worried about seeing like, hyperinflation take off, and not just hyperinflation, but because we already had hyperinflation essentially, but it's all locked up over here. So it didn't have the price impacts that it would have. It just had price impacts on like, bubbles.
We had hyperdebasement that has not shown up as hyperinflation. And
No. Inflation is what happened. The money supply was increased. That's inflation. Price increases are a related but separate phenomenon. And the media has literally decided to trick you about those terms.
Yeah, well, I agree, but it's again the free software issue, where it is like in the field of economics. I believe the term inflation means the price index, and debasement.
It doesn't.
Oh, okay.
In the field of economics, the monetary supply increasing, that's inflation. The monetary supply decreasing is deflation. Pricing is a value signal that is a related but independent phenomenon. Mm-hmm. And the reason it has to be understood as such is that if you have zero inflation or deflation in the monetary base, prices can still fluctuate greatly based on the belief in the future availability of either the money or the product.
Or
but
just
they are
things
not connected.
Like natural disasters, or
again, that's all about like social. That's all social faith.
Yeah,
things.
It has
that's like toilet paper. Everybody buys toilet paper when like COVID hit, which is really weird. It's not like it wasn't like Chinese self-shitting disease. It was COVID. It was a cold, and it was a coronavirus, right? So why everybody bought toilet paper the way they did was perplexing. But that's the kind of weird thing that you're going to get an effect somewhere, but you don't know what it is. Or like in China when they're like, oh, we're going to price fix eggs, and then they have a rubber boot shortage, and you're like, and you can trace how that went, but nobody could have predicted that. Mm-hmm. So, well, you're going to get shortages. You just don't know where they're going to pop up.
Do I have the book here, or is it in the other room? Let me see. Oh boy. I had to move all my books. I don't know where anything is anymore.
I think that the first CEO that will mention that they're going to slow down on spending on AI will give the green light to the others to say the same thing.
Well, that just happened
kind of like
OpenAI. They had a
Altman?
$1.4 trillion infrastructure outbuilding thing that they
again, he's like, that was an agreement, not a contract, so we're not actually
and so now we're only going to do 600 billion, which is also a totally realistic number.
Once you start seeing more of that, the bubble will pop.
Right. So there are options from the institutional perspective to prevent sort of this cascade of massive deflation on the institutional side and then massive inflation on the consumer side. It is like a panic reaction. They're going to have to find another bubble.
Yeah, they'll rotate it into. But I mean, some of it will go to crypto and gold for sure. But yeah, they'll probably try and rotate it into something else.
Right. Like you have to find another bubble if you don't want the pop.
I really hate working in crypto, dude. Just because every time I tell people I work in crypto, their first question, either they don't care or they don't understand, which is fine. Oh, here's the book I was looking for. Or if they are interested, they go, should I buy it? And I'm like, okay, I'm like, we are just looking at this problem from completely different angles. If that's your first question, right?
We have a couple of things. We have a few
and I don't want to say no
in,
because like the answer isn't no, but it's also like, okay, you're telling me so much about how you're thinking about this, and you and I are not interested in this for the same reasons, and we're not viewing this as the same thing at all.
On the other hand, you get to that point too where it's like people ask, well, how does Gadget Express work? And I'm like, you click the button and I explain on that level. I don't tell them unless it's somebody that knows how computers work already. What's this? A History of Money and Banking in the United States. Murray Rothbard. Wow.
Yeah. I read this book. So much of the history here. It's a pretty good book. I would say it's 4 stars, maybe 3. I'm a pretty rough grader though. So much of the book is just like the U.S. government tried to fix the exchange rate of gold relative to silver, and that caused a famine in Kentucky. And because there was a famine in Kentucky, all the cows in Kansas died, and because it's like, and then so what they did instead was they changed it, so now they're fixing the rate of silver instead of fixing the rate of gold.
And that caused a war with Mexico or some shit. And you're what?
Yes. That's the whole fucking book.
Well, just like, stop.
It's just, or it's like, some arbitrage happened and like it drove all the silver out of the United States, and then suddenly we need silver for some reason, and it's like all the silver is in France, so I guess we got to go to war with France now.
Right. Yeah. It's never ending. Mm-hmm. And you only accidentally get positive effects ever. You never get deliberate positive effects. You only get accidental ones. Pretty much.
You will get the positive effect, very, very muted for about like 3 weeks.
Oh, of a planned intervention, right?
Yes. For about 3 weeks, and then it gets completely dwarfed by some insane Cobra effect.
Well, you'll get something like, we're whatever. Silver's discovered in Southern California, and so everybody moves there, and then there's this massive influx of Chinese immigrants to build the railroad out and all that, and then there's like the silver crash because everybody has too much silver now because that's how the volume turned out, because you got taken out of the ground over here and put back in the ground over there, which didn't result in anything useful, and now the price of silver's in the trash because everybody has too much silver. However, you accidentally got a railroad out of it.
Yes, yeah, that is a thing that happens.
Which then the state, which helped screw all this up, winds up nationalizing in the end and breaking, and it's like, oh, that's good. Which triggers some other horrible event. It's never ending.
Oh,
anyway,
that's interesting.
Let's wrap this up, and we'll do part 2. What do you got? Elements of Algebra.
I was reminded. I just saw this book on my shelf, and I was reminded because of the Euler identity having to do with the complex numbers, and I was trying to see if I could quickly find it. And he doesn't call them imaginary numbers; he calls them impossible numbers. That's how it's translated.
Wait, one more time. Which numbers?
Instead of what we would call imaginary numbers.
Uh-huh.
He calls them impossible quantities.
Impossible. Well, is a quantity maybe.
Yeah, well, yeah. Again, this is English from this 18th century, or
This
this
is
is an English translation of 16th century academic Latin written by a Swiss German speaker living in Russia.
right. But instead of Leonard Euler, I really think we should call him Longhard Euler.
Oh. Oh, you know what? That could be a character that goes with big data.
Yeah. There we go. Longhard.
All right.
Longhard Euler.
I'm gonna work on that. I guess I'll let you get to work. I'll see you.
All right. Well, thanks a lot.